Mazowiecki, and we're co-organizing this with Wojtek. Wojtek, say hi.
Hi, I'm Wojtek.
So in short, I just wanted to, well, first I wanted to apologize for that, for April, that this didn't happen, but we hope to have the talk by Ben like in a couple of months, hopefully. And let me just say a few words that, well, the idea of this seminar is that last year we saw like many seminars, but they were all kind of similar. And well, in short, the idea was that we wanted to have longer talks with technical content rather than survey talks. And in this seminar, in general, the topics will be related to logic and automata, but possibly with connections to other areas like today. And finally, I wanted to say, I'm not sure how to say this, but somehow, usually after a seminar, you have this feeling that you heard about something new or even learned about some theorem. And here we wanted to somehow discuss like hot current topics. And like after the seminar, we hope that you have some feeling like, oh, finally, I know something about this twin whip that everyone is talking about. Yeah, so I'll let Wojtek say something now.
So what I would like to say is to say that we would be grateful for some feedback. Actually, two kinds of feedback. One feedback is if you have an idea about interesting topic you would like to hear on the seminar or about a speaker, we would be grateful for that. Best by email after the seminar. And second kind of feedback is so we have thought about it and we have proposed some kind of schedule which we think is the best for such kind of events, like 2 times 1 hour and a quarter plus discussion after that, but we are not sure this is not fixed. Yeah? So if you have any ideas about that, it would be better longer, it would be better, I don't know, divided to 3 parts or just in 1 part or a bit later. We are also happy to hear about that. So another thing is, yeah, so if you have any questions, please write them on the chat during the talk. Michał also told me that he will, from time to time, make some breaks, and there will be also moments to ask questions online, and you are encouraged to do that. And last but not least, I would like to say we encourage you to turn on the camera. We think it's better, it's more social and more encouraging for communication if you turn on your camera. And I think that's all on our side. So Szymon, could you please chair our meeting?
Okay, hello, welcome everybody. So it's my great pleasure to introduce Michał Pilipczuk. We are very fortunate to have Michał working as an assistant professor at the University of Warsaw. He is physically sitting right underneath me right now, so when he will be talking too long, I'll just stomp my feet and then he will stop talking, hopefully. We have the same view out the window. You can compare that, probably isomorphic view. So Michał is known for his work on algorithms, specifically parameterized complexity, graph algorithms, among other things. And he has received numerous awards for this work, including the Corbian Award and the Lipsky Award. And he has also been awarded an ERC starting grant, which has just started 2 months ago. And one of the goals of this grant is to understand structurally tractable graph classes. And this is very much related to the topic of today's lecture. So Michał, the screen is yours. Please go ahead.
Yeah, thanks a lot for the very nice introduction, and thanks a lot for the invitation to give this inaugural Friday afternoon seminar. Just to say, so I hope that this will be a longer and more in-depth talk with also ventures into technical details. So I'll try to be a little bit slower in more like a lecture mode rather than seminar mode. So in particular, you should probably hopefully see on the screen, I do not have proper slides, but rather I have my handwritten notes about the topic, and we will just go through those notes, essentially filling them in and discussing the stuff. So this is a sort of an emulation of a blackboard, let's say. Also during the talk, I will at sometimes pause for a minute to see if there are any questions in the room, and I will also ask you sometimes to, if there is some important definition or important lemma and you understood it and there is no problem so far, I will ask you to write a +1 in the chat so that I can see that there is some two-way interaction of nodding your head in this online way. Good. I hope that you see my screen and I am well audible, right? Shimon?
That's right, yes.
Good. Okay, good. So the topic I'm going to talk about today is TwinWiff, which is a new development in structural graph theory with very nice and important connections to logic and to model theory. So when I was asked by Wojtek and Philip what would I like to talk about on this kind of a seminar, I thought that maybe some older work is already a little bit not that interesting, but this is somehow a new development in structural graph theory, which is really, really exciting nowadays. And not so many people know about it yet, but many more people should. So this is also the goal of this seminar. So a little bit about the general story of what we are after in this area. So essentially, this is all about the interplay between model theory or let's say logic and structural graph theory or theory of structures. So essentially, we are looking at different kinds of logic of logical formalism in which you can express properties of various structures. And on the other hand, we have different classes of structure with different structural properties. And we would like to understand this correlation, this connection between some logical formalism being tamed on some class of structures. So of course, being tamed is not a really formal definition. You can understand it in different ways in terms of computational complexity, as we will usually understand in terms of expressive power, in terms of some combinatorial properties. But in general, there is a feeling that some logics on some classes of structures are tamed in the sense that you have a robust toolbox of dealing with problems expressible in this logic. So one the golden standard for this tameness notion that we will be talking about can be expressed in terms of computation complexity, namely the complexity of the problem of model checking, the logic on this class of structures. So the model checking problem is the problem where I'm giving a structure, say A, from my class of structures, and I'm giving some sentence of my logic L. Which expresses some property I would like to check, and the question is the sentence true in the given structure? Yeah, so just checking whether some property expressible in my logic is satisfied in the structure. And the usual goal of all of this work, this is like the golden standard of this problem being tractable, is fixed parameter tractability. So here we think about fixed parameter tractability parameterized by the given formula. So to unpack all this computation complexity talk, this means that I would like to have an algorithm whose running time is expressed like this. So there is some multiplicative factor that depends on the size of the formula, and then in terms of the size of the structure, I should be polynomial. And moreover, I should be polynomial with a constant exponent, yeah, independent of the formula phi. So I think all of the examples I'm going to give today, C will be equal to 1, which means that I want to have an algorithm that is linear time for every fixed formula. So for every fixed formula, I want to be able to test whether it is satisfied in the given structure in linear time. Of course, the multiplier then can depend on the form. Yeah. So this is the model checking problem that we'll be concerned about, and all of this theory can be of course understood on classes of relational structures or even more general structures. However, in order to make things concrete and easier to on the notational level, I will always talk during this work about graphs. Yeah. So in this talk, we will be talking about structures which will consist of vertices that can be pairwise. It can be adjacent in pairs. So the universe of the structure is always the vertex set, and there's one binary relation that selects all the adjacent pairs of vertices. So most of the stuff that I will be talking about is very easy to generalize to at least relational structures over binary signatures, so where you only allow binary relations. Good. So this is essentially the game plan for this whole area. So what do we know about possible approaches to getting this kind of fixed parameter tractable algorithm for the model checking problem? Essentially, there are two, well, there's a bunch of different tools for this, but essentially out of the high-level approaches, there are two concepts that need to be mentioned here. One of them is compositionality of various logics of interest, and the other one is locality. Yeah. So for compositionality, this is a very basic idea that if you have two different parts of the structure that sort of do not communicate with each other, essentially you can understand one of them, you can understand the second of them, and then you can somehow combine this understanding. So the natural example here would be the understanding of monadic second order logic on trees that you probably all have seen at some point. That if you would like to understand whether some formula phi, some sentence phi of MSO is satisfied on a tree, and say that this is the root of the tree and there are two subtrees at the children of this root, it suffices to understand what sentences are satisfied in the left subtree, what sentences are satisfied on the right subtree, and then you can combine this understanding into understanding what sentences are satisfied in the whole tree. Yeah, so obviously there is much more technical details behind it, but this is the basic principle. And then this understanding what sentences are satisfied in a subtree can be described by a bottom-up automaton on this tree, which gives you this classical connection between MSO on trees and automata. So this understanding can be then generalized for more general classes of structures, not necessarily trees, but structures that are more tree-like. So in particular, graphs of bounded tree width and graphs of bounded click width. These are graphs that sort of admit various tree-like decompositions on which you can employ the same principle of understanding subtrees of the decomposition and working your way up the tree in aggregating the information. Another kind of approach, which is most suited for understanding first order logic, is about locality. So essentially, the intuition is that when you have say a graph and you have two vertices in this graph, and these two vertices are far from each other, then any sentence that speaks something, say phi of xy, that speaks something about those two vertices, x and y, cannot really find a path between them if this path is long. Yeah, it can only say something local around x and local around y. Yeah. So this is the intuition that first order logic is local in the sense that it cannot see long connections between vertices. This intuition can be phrased, can be formalized in the form of so-called Geifmann's theorem, which gives you a linear time fixed parameter algorithm for model checking first order logic on, say, graphs of bounded degree. And this is the idea that essentially if you want to check whether some formula is satisfied on a bunch of vertices and these vertices are far from each other, you need to just understand how this formula, what are the logical properties of balls of bounded radius around them. So in graphs of bounded degree, these balls will be of constant size, so it is very simple to understand them. But then the simplicity of the neighborhoods can be understood via different tools, and then there is a long chain of results about first order logic and model checking first order logic on various classes of structures that are sparse. And sparseness here really plays a role in the sense that in sparse structures, you sort of expect to see many vertices that are far from each other, and therefore this locality can give you an edge in understanding how a first order sentence works on such a graph. Yeah, so this is basic locality toolbox. So this is the field so far, and now enters twinwidth, which is a new graph parameter, a new notion of, let's say, boundedness of or tameness of a graph, or of a graph class. And this new parameter sort of, at least in my head, it sort of combines the tools from both the locality and the compositionality approach. And it does it really nicely. So on one hand, classes of bounded twin width, or graphs of bounded twin width, also have, of bounded click width, also have bounded twin width. So graphs of bounded click width, they are sort of tree-like. They have a tree-like decomposition, but they do not need to be sparse. So in particular, bounded twin width encompasses all the structures that can be described in a tree-like fashion, but are not necessarily sparse. Yeah, we will go into the classes of bounded click width more closely in a minute. We'll do some examples there. This will be actually our main motivation for introduction of twin width. On the other hand, twin width also goes beyond structures that are tree-like, in a sense that if you look at the click width, you really feel that there is a power in this parameter, in the sense that it describes general classes that are not necessarily sparse. However, you are still constrained to the fact that your structure needs to look like a tree. Bounded twin width gets rid of it in the sense that it also encompasses not tree-like structures. So, for instance, planar graphs, or even all proper minor closed classes, so all classes that exclude a fixed minor, they have also bounded twin width. So, for example, grids, a classic example of a structure that is that doesn't have bounded click width or bounded tree width, a grid actually has bounded twin width. So from the point of view of twin width, it is also tractable. So now comes the corollaries, the results somehow of this new definition, that model checking first order logic on graphs of bounded twin width is actually fixed parameter tractable with linear time dependence on the size of the structure. So there should be some asterisk here saying that actually you need to be given a suitable decomposition to make this work. But if you are given a decomposition, then you can perform FO model checking in linear time. So it somehow combines these two branches. On one hand, bounded click width kind of approach of aggregating information along a tree using an automata approach. On the other hand, let's say locality approach that is inherent to sort of sparse structures. And finally, and probably most importantly, this is not an artificial merge of, let's say, bounded click width and planar graphs or grids. This parameter is supernatural. It's once you see the definition, it's actually kind of surprising that we did not come up with this like 20 years before. So this really fits the picture very nicely, and yeah, in my opinion, this is a breakthrough in a conceptual understanding of what does it mean well-structuredness for a graph from the point of view of model theory. Good.
Michał?
Yes.
I don't know if you said it, but when was it introduced?
Yes. So sorry. It was actually introduced last year, yes, in 2020. So okay. I was just going to say this.
Okay.
So this parameter is super new. So the first paper, the Twin with One paper, due to Edouard Bonnet and Jun Kim, Stéphane Thomasse, and Rémi Vatrigan, was I think put on archive in April 2020. So last year, and like this whole field exploded at this point. So then we have this group from France started developing this theory more. So now there are TwinWiff2, TwinWiff3, TwinWiff4 papers and some other offsprings around. And it seems that this theory of TwinWiff is really rich on various fronts, from the perspective of combinatorics, from the perspective of algorithm, and from the perspective for this purpose of this talk of model theory. So this is really something exciting and that is developing very quickly recently. Good. So the plan for this seminar is to give the following. So first of all, I need to introduce to you TwinWiff. We need to give some definitions, intuitions, some examples, and see how this parameter really works. Then I will be speaking about a more combinatorial aspect of this, namely connection to so-called mixed minors. And there is a very important duality theorem for TwinWiff that gives you an understanding that that on one hand there is the composition that witnesses that there is bounded TwinWiff. On the other hand, there is some obstacle for having bounded TwinWiff, and this kind of an obstacle decomposition theorems are very important for understanding various graph parameters. And finally, during the second half of this seminar, I will present the algorithm for model checking first order logic. So as you see here, in this list of the authors of those TwinWiff 1 up to 4 so far papers, my surname is not there. I hope to be quite soon there in those dots down there. So we are working on TwinWiff here in Warsaw for, let's say, the last year. I hoped to have some tangible results out by the time of the seminar, but you know all probably how it works with putting the finishing lines on your papers. So we are working on the model theoretical aspects here of TwinWiff together mostly with Szymon Tojuńczyk and with Jakub Gajajski, but also with other people on some other aspects. Okay, but because I was working on TwinWiff for the last year, I thought that maybe I can share some of my understanding so far with you. This probably understanding will be a little bit from a different perspective than the talks of other people that have, for example, Edward Bonnet, who was speaking several times on different occasions about TwinWiff. So maybe this perspective can be also beneficial if you have seen already something about TwinWiff before. Good. Okay, so this was for the introduction about what the seminar will be about. Maybe there are some questions at this point. Okay, I see already some +1s. It's good that you, see how this works. Good. So now we are going to work our way towards the definition of TwinWiff. And I would like to start with recalling or introducing the definition of ClickWiff, because I think that starting from ClickWiff actually gives a good idea of what TwinWiff is trying to model. So just to recall, in the ClickWiff setting, we are working on graphs, and we are more precisely working on graphs that are k-colored. So every vertex is in one of k colors. So for example, here you have a schematic depiction of a 3-colored graph, so a graph where every vertex is either yellow or red or blue. So now on such graphs, you have different kinds of operations, of algebraic operations. So the most important operation is the operation of joining two graphs. So when you are joining two graphs, you are given already two already constructed k-colored graphs, graph number 1 and graph number 2. Yes. And you are sort of smashing them together, so you are putting them next to each other, and let's say making this joint union of the universes of the vertex sets, and then the colors merge naturally. Yeah, so for example, yellow is being merged with yellow, red with red, and blue with blue. And when doing the join, you can also specify that you will add some edges between the two sides, yes, of this graph, between G1 and G2. So for example, you can say when doing the join that, for example, every guy of color blue on the left side will be connected with every vertex of color red on the right side. And maybe every vertex of color yellow on the left side will be connected to everybody of color yellow on the right side. And maybe also to every vertex of color red. So it is important now that all vertices on one side of the same color, they all behave in the same way, in the sense that they will always have exactly the same neighborhood on the other side, because the adjacencies that we are introducing only depend on the color of a vertex and not on the individual vertex. And then you have also the operation of recoloring, so you can change the colors. So for example, you can even smash the color. So here you are making a recoloring where blue is kept as blue. Red is being recolored to blue. So now the blue vertices sort of merge into one blue box, and yellow is being recolored to red. Yeah? So the join operation is a binary operation. Yeah? It takes two graphs. Recolor operation is a unary operation. And there is also a nullary operation called a vertex, and it allows you to just introduce a vertex of some color. Yep. So now we have a binary operations, unary, nullary operations, and you can start to construct graphs using those operations. So you start with nullary operations that introduce various vertices, and now you can merge them using joins. You can do recolorings on them, and in this way you can construct from smaller graphs larger and larger graphs.
So sorry. So if you add this vertex, this one vertex, do you fix a color of this one extra vertex in this unary operation?
Yes. Yeah.
But,
in this
can you
operation. Yes.
But so you actually have, like, if you have k colorings, you have k many unary operations.
Yes. Yeah, we have k many nullary operations of introducing vertices of different colors. We have actually k to k operation for recoloring, depending on the recoloring that we apply, and we probably have something 2 to the k square join operations depending on exactly this data of who will be connected to whom. So formally, this algebra has this kind of a signature. Yeah. Any more questions? Okay. If not, then let's go further to click with, and the click with is just the minimum k for which there is a so-called k expression constructing a graph. And k expression is simply a term or a tree consisting of those operations. In the leaves, I have individual vertices, and then on the in the internal nodes, I have the operations that aggregate larger and larger subgraphs until the whole graph is being constructed. So of course, here we are talking about uncolored graphs. So the click width of a graph is the minimum k for which some k coloring of it can be constructed using this algebra of k expressions. So I hope that for many of you this was a reminder of click width. If you did not see click width so far, maybe here is an example. So the example is actually an important example in this whole area, a half graph. So a half graph is a bipartite graph where there are two sides of the bipartition, the A side and the B side, here blue and red, and I put an edge between a vertex AI and a vertex BJ if and only if I have inequality between the indices. Yeah, so the edges on this picture go always from top right to bottom left, like that. So I claim that half graphs have click width actually probably at most 3. And for this, I just need to make a free expression using 3 colors that construct a half graph. So how do I do it? So maybe we'll not go into very much details because this will be intuitively, hopefully clear. So you can essentially construct such a half graph from left to right. So at every point you have already constructed some prefix of the vertices A, some prefix of the vertices B. Yeah, so here blue and red, and you want to construct the next rung of this half graph. Yeah. So how do you do it? You first introduce, let's say, the next vertex A here, yes, in some new color, say green. And then using the join operation, you join it with the rest of the graph. And in this join operation, you can make this vertex adjacent to everybody on the other side. Yeah. So now once this vertex is constructed, you can now recolor it. So you join it to all the blue vertices. So you recolor color green to color blue, so that now this vertex is again in this is in this big cloud of blue vertices. And now you can introduce the corresponding B vertex. So you again introduce now another vertex of color green, and you join it with the graph introduced so far, making it adjacent. Actually, I should be doing it that way around. I'm very sorry. Yeah. I am first introducing the vertex B here, making it non-adjacent to everybody in blue, and then joining it with the red vertices, and then I am introducing again a green vertex on the other side, and I'm making it adjacent to all the red vertices. And again, I'm forgetting about its color by merging it into this cloud of blue vertices. So in this way, I have constructed a half graph from left to right using only 3 colors. So this gives me a bound on the click width, the click width is at most 3. Actually, even a parameter called linear click width is at most 3. A linear click width is a linearized version of click width where this decomposition needs to be sort of linear. Formally, whenever you're making a join, you are making a join with a single vertex. Good. Is this clear, or are there any questions about click width? Maybe you can put a +1 in the chat so that I am happy with seeing it. Okay, I see that the understanding is there in the room. Even somebody has +2. Good. So yeah, so then as I already have mentioned, click expressions, so these terms constructing graphs can be viewed as essentially labeled trees. Yeah, so you have a tree of those operations, and each operation is either a unary operation, which is a recoloring, or a binary operation of joining two graphs, or you have also leaves that introduce individual vertices. So yeah, the leaves are the vertices of the graph, while the internal nodes are the operations performed in the click expression. Yeah. So now it's if you have this tree-like point of view, it's interesting to understand what is a subtree of such a decomposition. So say a subtree looking like that. So a subtree looking like that has some leaves that correspond to vertices that are introduced in this subtree, and there are also vertices that are outside of this subtree. Yeah, and the subtree is constructing some subgraph, some induced subgraph of this graph. Yeah. So if you look at this, here is this subtree. Here are the leaves of the subtree, somewhere here. Yeah. So these are the vertices there, and you would like to understand what is the interaction between the vertices in the subtree and the vertices outside, yeah, in this context in which the subtree is being immersed. Yeah? So these vertices here in the subtree, when they sort of are during this construction procedure where they leave this subtree and start to interact with the other vertices, they leave within at most k colors. And each of the colors is, from the point of view of the outside, it is indistinguishable. These vertices behave in the same way when they are being checked against other vertices. So this means that the subtree of the decomposition gives you a cut in the graph, a partition of the vertex set into stuff in the subtree and the stuff outside of the subtree, so that the guys inside the subtree can be partitioned into k classes corresponding to the colors, and these vertices in each of those classes, they behave in the same way with respect to the outside. So vertices from the same color will have exactly the same neighborhood outside here. Yeah. So this subset of vertices, this color will, for example, see some half of those vertices outside, but not see the other half. Yeah, and all of them will behave in the same way. So this means that because here I have k different classes, yes, each of them has some neighborhood. Yes, I can draw all of those neighborhoods, and this means that the right-hand side can be also partitioned into at most 2 to the k classes, depending on what classes they see on the left-hand side. So this means that the subtree of the composition is sort of a cut of a small diversity, in the sense that I can cut the graph in such a way that on both sides of the cut, I see only a bounded number of different behaviors, in a sense, with respect to the other side. So you can, yeah. Okay, I thought there was some question. So you can think now, what does it mean for this construction process? So in the construction process, when you are doing this construction of the graph, say bottom up on the subtrees, at every point you have already processed some subtrees of the graph, which results in some colored graphs. Here they are being depicted by those blobs. Yes, and each of the blobs is being partitioned into k parts, at most k parts. Yes, so that the parts behave in the same way with respect to the outside. So this means that if I have 2 parts, let's say this part here and this part here, from 2 different subtrees, yeah, the interaction between is so-called pure, in the sense that they are either complete, everybody from here is being adjacent to everybody from there, or 2 different parts can be anti-complete, in the sense that nobody here from here is incident to nobody from there. Yeah. So this means that parts from different blobs, different subtrees, are pure to each other, which means that they are either complete or anti-complete. And the only non-trivial interaction, so like impure interaction between the parts, can be somewhere within those subtrees, because these are interactions that were constructed before in this K expression. So I wanted to go through this understanding of click with here explicitly, because this idea of pureness of interaction between different parts of the graph is essential for understanding the intuition behind twin. Good. Any questions about this?
I have one. I mean, the most active participant, right? Sorry for that. So, you know, it looks like a little, at least to me, it looks like a little bit that this coloring has something to do with types, right? These Q types from yesterday. Is that true? You know,
you are probably now talking about the There will be a lot of meaning in bounded click with. Indeed, there is you are right that that these colors. If we'll be talking about transactions and interpretations during the second half of the lecture, and there it will be clear that the colors correspond to types.
Thanks.
Yeah. Good. Okay, so now we can sorry?
In the chat, there is some comment that actually what you introduced is
NLC with.
Yeah. Could you comment on that?
Yeah, so essentially with click with, as with many other parameters, there are 5 competing definitions in the literature. There is click with, the definition introduced by Kursel. There is NLC with, there is, I think, modular with, which is also equivalent. All of these notions are equivalent up to functional equivalence. I think maybe the one that I just introduced was NLC with, indeed. All of them are essentially equivalent. You can choose the one that suits you best. From the point of view of, say, model theoretic questions, all of them are equivalent. Okay, so about the definition of twin width. So now we are going to make this idea about various parts of the graph interacting in pure or impure way much more concrete. So for the definition, I need to introduce, of course, a few definitions, and one object that we'll be speaking about a lot is a so-called trigraph. So a trigraph is just like a graph. So there are some vertices and there are some connections between them. But now there are three different types of connections. There can be edges. I will usually depict them in blue. Yeah. There are non-edges, as usual. Yeah. So whenever I do not write something, it is a non-edge. And there are also so-called red edges or error edges that depict that somehow there is some complicated interaction between two vertices. Yeah. So either for every two vertices, either they are not connected, and that's considered somehow simple, or they are connected, and this is also considered simple, or the relation between them is complicated, let's say. Yeah. So there are three types of adjacencies here. So now if you have such a trigraph, you can think about contractions in a trigraph, or rather the identification of two nodes. So whenever you have two vertices of a trigraph, for example, this one and this one, yes, you can think about identifying them. Yeah, so then you just merge them into one vertex, and you smash the edges incident to both of them naturally. Yeah. So for example, in here, if I identified U and V into one vertex, then there would be some adjacencies that need to be somehow reconciled, and the reconciliation is somehow very natural. So whenever you've got this vertex here, these two vertices, and for instance there was a vertex here that was incident to both of them, yes, then clearly this vertex should be incident to the contracted vertex, yeah? Because still it is clear that this vertex is simply adjacent to both of them, so to the merged one as well. Yeah, so an edge plus an edge is being reconciled into an edge. Yeah. Whenever there is an error, so there is a complicated interaction between one of those vertices and some vertex outside. After the contraction of the vertex UV of the two vertices UV into one, there will be an error. Yeah, because at least one of those interactions was complicated, so the interaction afterwards is also complicated. And finally, if there is a vertex here that is adjacent to one of them and non-adjacent to the other, yes, then both of these interactions are simple by themselves, but after contracting UV into one single vertex, I do not know how to reconcile it, this edge and non-edge, and therefore I'm putting an error. So the errors can arise by smashing a non-edge with an edge. Good. So maybe, so now if you start with a graph or a trigraph, you can make various contractions. You can contract some pair of vertices, some other pair of vertices, and so on and so on. And the contraction sequence for a graph is just a sequence of contractions that ends in a single vertex. So maybe before I let you make any questions about this process, because this is really important, this contraction sequence, I would like to make a larger example of a contraction sequence, and in particular a contraction sequence of a grid. So I did not prepare any picture here because for this we will use some external software. So do you see now a grid on the screen?
Can I interrupt just to be sure?
Yeah.
When you identify two vertices with non-edges, then this gives a non-edge.
Yes. Yeah. Okay. I said two edges merge into an edge, and of course two non-edges also merge into a non-edge. Good. Good. So here, do you see on the picture a grid?
Yes, we do.
Yeah. Yeah. So this is a twin-width editor that was implemented by our friend Felix Reidel when we were discussing twin-width. And here you can essentially model those contractions so that you see how they work in practice. So here is a grid. So far, we start with a graph. So all the edges, I have only edges and non-edges in the graph. So how to make a nice contraction sequence of a grid? For example, let's say that I take the vertex A and I contract it with B. Yeah. So now I contracted it to a single vertex AB and observe now that towards all the vertices that where the adjacencies were differing between A and B and those vertices, I have now red connections. Yeah, because now an edge got smashed into with a non-edge. So now I have contracted it like that. So now I can try to think about the first row of the grid, and I can contract it in pairs. And I can collapse the first row of the grid. So now I can, for example, contract C with D, getting something like that. Then E with F, and then G with H. And in this way, I have collapsed the first row of the grid. And from the second row, I have now this sort of a comb of red edges. Yeah, so this red graph here is possibly large. It consists of the whole row, but the degree is bounded, and the degree is what we will be carrying. So now I can collapse the second row. Yeah, by collapsing like a matching. Yeah, and in this way, I am left with just one row and again a red comb. So now I again contract in pairs. Yeah, I finish with a red path. So now I can contract it from left to right, and I ended up with a single vertex. Yeah. So this is a contraction sequence, and you can, as you see, what we care about during the contraction sequence are the red edges that appear during the process. So, is there any question about contraction sequences, or otherwise, please put a +1 if this is clear. Yeah, there is a comment by Dimitrios that contraction is a little bit misleading because it's identification of two vertices that are possibly far from each other in the graph. It is indeed true. However, I just stick with the original terminology introduced by Bonnet et al. Good. Yeah. Okay. I see some +1s. So let's continue. Okay, so now a width of a contraction sequence is just the maximum red degree that I observed during this sequence. So yeah, so whenever I'm doing those contractions, some red edges appear. They can be all over the place. But what I care about is that every vertex of my trigraph needs to be adjacent to at most a bounded number of red edges. Yeah. So in a sense, in this contraction sequence, I can have a lot of errors all over the place, a lot of complicated, already forgotten interactions that are complex. But I want every particular part of the graph, every particular vertex of my trigraph, to be incident with only a bounded number of errors. Yeah. So this is a good contraction sequence. Is a contraction sequence that has maximum error degree bounded. Yeah, and the twin width of a graph is just as usual the minimum possible width of a contraction sequence. Yeah, so a graph has bounded twin width if I can contract it to a single vertex by keeping always the red degree, the number of incident red edges bounded by a constant. So for instance, the contraction sequence for a grid that I showed you in this editor, you can easily see that I have never got any vertex of red degree larger than 4. So this contraction sequence gives you a bound that the grids have twin width at most 4. Good. Good. So this was the definition of twin width. So let's observe. Let's look a little bit more and at what happens during those contraction sequences. Yeah. So whenever I'm doing a contraction sequence, yes, I've got at every point I've got some trigraph. Yes. And what are the vertices of those trigraph? Well, as we have seen already in this editor, essentially whenever you are identifying a pair of vertices, you can think that now this becomes a bag consisting of those two vertices. vertex. And now if this being identified with somebody else, then somebody else is joining this back, and so on and so on. So whenever you have a trigraph somewhere during this contraction sequence, then the vertices of this trigraph are essentially sets of vertices of the original graph G that form a partition of the vertex of G. I will call those sets of vertices sometimes blobs or parts or whatever. Yeah. So this is the usual situation during the contraction sequence. Yes, I've got some partition of the vertex set of the graph into blobs. Yes, and I have some connections between them. And you can easily see that what happens when will you have an edge between this part and this part? Well, in order for this edge to be there, you need to have an edge between everybody here and everybody there, because otherwise, if there are both edges and non-edges, they would be smashed into an error. Yeah. So an edge between two blobs corresponds to the blobs being complete to each other, and a non-edge between two blobs corresponds to blobs being anti-complete to each other, not surprisingly. And finally, an error edge between two blobs means that there is some more complicated structure of adjacency between those two blobs. If somebody is seeing somebody on the other side and somebody else is not seeing somebody on the other side. Yeah. So errors correspond to mixed or impure relations between different blobs. Good. So this is how twinwidth is defined, and it is really about contracting the graph into a single vertex while keeping the number of complicated interactions bounded, incident to every particular part. Okay, so let's see some more examples. So we have already seen that grids have twinwidth at most 4. This we already seen. Actually, we've seen also that paths have bounded twinwidth. Well, because a path you can contract essentially from left to right. We have actually done this during the grid. In the grid example, if you contract a path from left to right, you see only a red edge on the far left, and this red edge is being pushed somehow during this contraction sequence. So for a tree, why trees have bounded twinwidth? So it is also quite simple to see. So if you have a tree looking like that, you can first start with looking at all the leaves. And whenever you have a bunch of leaves with the same parent, you can contract all of them into a single one. So all those bunches of leaves you can contract to single vertices. Yeah. So whenever you see a bunch of leaves with the same parent, you contract them one by one. Yeah. So in this way, you have a tree looking like that. And now it is tempting to just say each of those leaves is being contracted with its father. Yeah, with its parent. So if I now contract this vertex with this vertex, yeah, I end up with the contracted vertex, but this edge is getting red. Yeah, because the root was seeing one of them but not the other. And similarly, if I contract this one to this one, this edge will also become red. So if I now contracted all of those children on their parents, then suddenly the root would have a large red degree. So you need to be a little bit careful. So now, after contracting two of them, you can identify them, yes, into a single vertex, thus getting one vertex with still one red edge. And then you can again do a contraction, get another red edge, and contract those two, and so on and so on. Yeah, so you need to be a little bit careful for the trees. For graphs of bounded click width, you can take this idea from trees, and you can lift it quite easily to graphs of bounded click width. So essentially, you will contract bottom up along a click expression. Yeah. So it is a little bit. I mean, you need to stare a little bit on this to see that this will work. The main idea is that whenever you are doing the contraction bottom up, yes, yeah, you have the whole click expression, which you can view as a tree, yes, and so far say that you have contracted those the leaves in those violet subtrees into you have contracted those violet subtrees. So each violet subtree, yes, you will not contract to a single vertex because then, well, the interaction between different violet subtrees can be still impure. But you know that each violet subtree here, the leaves in it can be partitioned into at most k classes, which interact in a pure way to the ones outside. So more precisely, we have already seen that each of those subtrees, I can see it as a set of vertices here that can be partitioned into at most k classes, yes, that have a pure interaction to the parts from the other subtrees. Yeah. So in the what you will keep during the contraction procedure, you will keep each of those colors, each of those classes as a separate blob, yeah, in a trigraph. And now you know that the interaction between blobs from different subtrees is pure. You will never see a red edge between blobs originating from one subtree and blobs originating from some other subtree. Yeah, the only impure interactions can be within subtrees. So the red edges in this contracted trigraph can only appear within those subtrees. Yeah, and now you need to look a little bit closer at what happens if you now merge two trees into a larger tree. Then essentially this corresponds to merging two of such clouds of blobs into one and performing appropriate contractions between blobs that are in there. Yeah. So in particular, this means that errors between different blobs are only within the subtrees. So the error graph, the graph of the red edges, has all the connected components of size at most k, right? Because they are always confined to those blobs. So not only in bounded clique-width I have degree, the red degree is bounded by k, but even the maximum component size is bounded by k. And then there is an easy exercise, which is actually quite insightful, that you can actually define clique-width in this way through contraction sequences. A graph has bounded clique-width, or say a class has bounded clique-width, if there is always a contraction sequence when I do not care about the maximum red degree, but I do care about the maximum size of the components of the red graph. Yeah. So clique-width now can be understood in terms of these contraction sequences by redefining the width measure to be the largest size of a red component. Good. Are there any questions to these examples? And otherwise, please put a +1 so that I'm confident that you are on the same page.
So yeah. What's a red component?
Yeah, so we have this trigraph, yes, of the blobs. Yeah, maybe I should be more. I should have been more specific. I have some edges and non-edges, so these are pure connections. But what I care about are the red edges, the errors. Yeah. So the red component is a connected component of the graph consisting only of the red edges. Yeah. So in here, for example, this would be one red component. This would be another red component.
Okay.
And here I've got two trivial red components. Yep.
Okay, thank you.
So somehow both edges and non-edges are considered simple and do not appear as problems for us. Yes, we care about the complicated interactions. Okay, good. I see some +1s, so so we continue.
Can I ask something?
Yes.
Yeah. So you said the error graph has component size at most k, but probably it's 2k when you merge, when you try to make a string union.
Yes, so you need to be a bit more careful. So I said here, yeah, probably 2k here would be okay, because at this pure stages, when I'm done with a subtree, this will be actually k. But then when you are looking at this particular merge, when you want to merge two components, temporarily you can create components of twice larger size. That's correct. Yeah, but still,
thank you.
it is okay for this exercise in the sense that bounded click width is the same as having bounded maximum size of a red component. So because in this statement we do not care about the times 2 factors. Yeah, only about boundedness. Okay, so let's see how this notion of bounded twin width fits within a larger picture. Yeah. So what are how it corresponds to let's say other well-known notions of structuredness in graphs. So first of all, we have already seen that grids have bounded twin width. And therefore, it should not be that surprising that if grids have bounded twin width and trees have bounded twin width, then you can go for planar graphs. So planar graphs have bounded twin width. It's actually surprisingly non-trivial to prove this, and that this is the case. We will see an argument later on. Not full argument, but at least a convincing enough, I hope. And more generally, if you go a little bit further, planar graphs are exactly K5, K3, minor 3. Yeah, so you can generalize it to saying that whenever you exclude some fixed graph as a minor, H minor 3 graphs, they have also bounded twin. Yeah, so in the hierarchy of sparsity, in the sense, all these topologically constrained graph classes, say graphs embeddable in a fixed surface, they all have bounded twin width, and therefore twin width, boundedness of twin width goes well beyond tree-like structures. Yeah? On the other hand, the caveat is that if you look at graphs of maximum degree 3, yeah, so graphs of bounded degree in particular, quite surprisingly, they do not have bounded twin width. They are already much richer. Well, maybe not much richer, but they are already richer than bounded twin. This is also a quite interesting statement. We actually do not have a direct proof of this. So I will comment on this later on. There's only a counting proof. We simply can count that the number of graphs of maximum degree 3 is simply larger than can be in any class of bounded twin. So there is an open problem of actually making a precise construction of graphs of maximum degree 3 that has an unbounded twin. Yeah. So this is how this notion fits within the let's say non-tree-like but sparse structures. Good. So for the remainder of this first half of the talk of the seminar, I would like to talk about the connection with mixed minors. So this is a matrix point of view of on twin width, which is really important when you are working with like the technicalities of this notion. And the main idea is that bounded twin width in terms of defined as we have seen it via contraction sequences is equivalent, quite surprisingly, with the possibility of nicely organizing the adjacency matrix of the graph, so that you do not see some forbidden structure. And this really gives you a nice handle on how to construct those contraction sequences, because we will this will be used for showing that if you are able to organize the adjacency matrix nicely, then you automatically will have bounded twin. Good. So there will be kind of a duality theorem for bounded twin width in terms of an obstacle through organization of adjacency matrix. Yeah. So let's go into this. What are mixed minors? So imagine that you have gotten a graph. Yes? And in order to speak about the adjacency matrix of a graph, I should probably define an order on the vertex. Yeah, because the rows and the columns of the adjacency matrix are typically ordered somehow. So we will be working here also on ordered graph. So an ordered graph is simply a graph together with a total order on its vertices. And given such an ordered graph, I can think about this an adjacency matrix of this of this ordered graph, where I just, as usual, put a 0 or a 1, depending whether there is an edge or not. Yeah, 0 or 1, and so on. So now imagine that you've got this adjacency matrix, and those mixed minors will be about partitioning of columns and rows. So a convex partition of, say, columns is a partition of the columns into intervals in the order, yes, which I will call also blocks. Yes. So by convex, I mean that every part of the partition needs to be a convex interval in the ordering imposed on the graph. Yeah. So imagine that you've got a convex partitioning of rows and a convex partitioning of columns, here depicted in red and blue suitably. Yeah. So now this when you have this these two partitionings, yes, this nicely somehow partitions the whole matrix into those squares here, yes, which I will call zones. Yeah, so each of those is a zone. So a zone is an intersection of a block of rows with a block of columns, yeah, from the partition. So such zones can be of various degree of complexity. So the easiest zones are zones that are pure in the sense that are constant. Maybe there are only zeros in the zone, and maybe there are only ones in that zone. So these are constant zones. There can be also zones that are horizontal or vertical. So a zone that is horizontal is a zone that looks like that. Every row consists of only of ones or only of zeros. Yeah. Or in other words, it is just the same column repeated many times. Yeah. So this is horizontal zone, and the vertical is simply symmetric. Yeah. And all the other zones, so these are kind of zones that are really, really simple, either completely homogeneous or at least homogeneous in one direction. Yeah. And all the other zones will be called mixed. Yeah. So mixed zones are zones where you essentially see at least, say, two different rows and two different columns. Yeah, so not particular, a very difficult definition. Okay, so now a k times k mixed minor in such an ordered graph is a pair of convex partition of partitioning of rows and of columns. Yeah, where every zone into k parts. So here are k parts in the partition P and k parts in the partition Q, and every zone here should be mixed. Yeah. So somehow this is a way of seeing one partition of the vertex set of the graph and another partition of the vertex set of the graph, where every pair of parts, one from one partition and one from the other partition, they are complicated with respect to each other. Yes, they are neither horizontal nor vertical nor constant, they are mixed. So this is a k times k mixed minor. Yeah. So now comes the theorem, and this is a theorem from the twin width one paper. Yeah, that says that twin width can be defined through the existence of such mixed minors. In the following sense, through not the existence, but through forbidding such mixed minors. So if you have a graph of twin width at most d, then you can make an ordering on the vertex of a set of the graph, such that you will not see a large mixed minor. Yeah. So if the twin width is at most d, then there is an order on the vertex set such that you will not see a 2d plus 2 times 2d plus 2 mixed minor. Yeah. So on one hand, if you have bounded twin width, then you can organize the adjacency matrix nicely. On the other hand, if there is an ordering where there is no k times k mixed minor, then actually you can produce a contraction sequence. Yes, the graph has bounded twin width, bounded by some function of k, which is actually doubly exponential in k. Yeah. So this gives a weak duality correspondence between twin width and ability of organizing the adjacency matrix. So you do not see this. So you do not see this complicated structure in the organized adjacency matrix. So the intuition here is that one is actually pretty simple. The important part of this theorem is point number 2. because this is a way of constructing a contraction sequence for a graph out of a total order on its vertex. So in order to prove that graph has bounded twin width, it is very often much simpler to find a nice order on its vertices that doesn't have this kind of an obstacle. And from this, automatically, you get a contraction sequence, well, maybe of slightly larger width here. But very often it is the case that finding a good order is simpler for particular cases than trying to get a contraction sequence. In particular, this is the case for H minor free graphs or for planar graphs, as we will see later on. Yeah. Any questions? I see that Dimitro has a question.
Is there a purely graph theoretic way to express this abstraction instead of matrices, just some kind of relation between graphs?
You mean this mixed minor?
Yes.
So actually, here when we are working, we do not like to work with matrices because it's a little bit complicated. You can often see it as a bipartite graph. So from a graph G, you can make a bipartite graph by making 2 copies of G, and whenever there was an edge bit in here, you can make here 2 edges like that, like a cross. So this is a standard construction. And then what this corresponds in the form of this bipartite graph, this is a part. So one partition is a partition of one side. Second partition is a partition of the other side. And then this mixed means that not precisely, but it morally means that the sides are impure towards, the parts are impure towards each other. This is not really the case in the sense that this horizontal and vertical matrices are actually impure, but are from the point of view of a mixed minor considered simple. But morally, this is how how you can sort of intuitively view this.
Okay, thanks.
Yeah, but it is important that this partition can be different. So viewing it from the point of view of a bipartite graph actually gives you some better understanding of this.
Yes, but it's also important that it's convex, so into intervals. So it's not a purely graph theoretic description. It involves the order.
Yes. Yeah. Having an order on this is actually very, very important for all of this.
So it probably cannot be purely translated graphs because of this.
Yeah.
Yes, and as Anush pointed out, the 2 orders on the 2 sides are the same order.
Yeah. Yes. Yes, indeed. Good. Okay, so my plan is to have this first part slightly longer, and so I will probably take 10 or 15 minutes more of your time here, and then the second part will be a little bit shorter. It is also a little bit more lightweight. But now I would like to give you a sketch of the proof of this theorem. Yeah. More precisely, one is actually pretty simple, and we will go through it very quickly, just to give you an idea where this order comes from. Yes. But point number 2, the really important part, actually uses very nice combinatorial tool that is really important in all of this business. So for point number 1, now we want to prove that if a graph has bounded twin width, then I can find a nice order on its vertex set so that the adjacency matrix doesn't have a large mixed minor. Yeah. And the idea is to, how do you define this order? The idea is that you essentially reverse the construction sequence. Yeah, so the contraction sequence ended up with all the vertices being put into a single blob. Yeah, and now immediately before, this blob was being obtained by identifying 2 smaller blobs. Yes, each of them resulted from identifying 2 smaller blobs, and so on up till you get individual vertices once you reverted this whole contraction sequence. Yeah, so you can also think about this contraction sequence in the form of this kind of a tree, but you need to be very careful about this because the contractions happen in time, in a sense. So these blobs they actually do not live at the same moments of time, may not live in the same moments of time, and there can be some red edges between them. So you need to be very careful when you are working with bounded twin viewed from the point of view of this unraveled contraction sequence.
So in a sense, this tree-like structure is also ordered.
Sorry?
So this means that this tree-like structure is ordered structure. It's not just a tree.
Yeah. So when I'm doing this unconstruction of this bag, yes, I am telling who is the left child and I'm telling who is the right child. I'm doing it arbitrarily. So in this way, whenever I'm uncontracting and saying this will be the left guy, this will be the right guy, at every point I'm getting some order on this. And in general, this gives me a total order on the leaves, which is my order on the vertex. So the important part of this construction is that I want every blob, yes, which comprises all the leaves that it is uncontracted into. I want every blob to be convex in the final order. Yeah, so every blob that appears at any point during the contraction sequence needs to be convex in the constructed order on the vertex. Yeah, so I unravel the contraction sequence in any way, and then I make a linear left to right ordering on the children so that every subtree is convex in this order. Yeah. So now essentially what you need to do, you need to stare at this order for long enough and convince yourself that it's good, in the sense that it doesn't have a large mixed minor. And how do you prove it? You assume that there is a large mixed minor, say consisting of a row partition P and column partition P and row partition Q. And then you need to look at how this mixed minor interacts with this contraction sequence. And this is a little bit technical. You essentially apply contractions until the first moment when one of those blocks of either this partition or this partition is being completely contained in a single block. And if you stare at it long enough, then you will actually see a contradiction. Yeah. So this is a good order. So just this was a sketch showing that in order to get a good total order on that in a graph of bounded twin width, you need to unravel stuff and then like reverse the contraction sequence and then make any left to right order on the leaves. Good. Yeah, Dimitri, another question.
Yes, so I guess this procedure doesn't give a polynomial time algorithm that either finds the minor, the mixed minor, or finds the identification sequence, even with big parametric.
Well, it's getting a contraction sequence is like here we are assume that we get a contraction sequence. Yes, it's the other implication.
In order to find the contradiction.
I do not get it.
No, my question is if you can turn this to a polynomial time algorithm.
Like you can definitely turn it into a polynomial time algorithm that gets a contraction sequence and outputs an order on the vertices. This is fine.
Or finds a mixed minor.
Or finds a mixed minor, yes.
Okay.
Yeah. Well, yeah. But, meaning assuming the contraction sequence did not have large red degree, there will be no large mixed minor. No. Good. Good. So now I will try to sketch in the remaining 10 minutes the proof of point number 2. Yes. So this interesting implication. So the implication from that there is a good order, that this implies that there is a contraction sequence. Yeah. So now we are given just a graph with a good order without a large mixed minor, and we are going to produce a good contraction sequence for the graph. And the main ingredient in this proof, and this is something that a result that really underlies a lot work in TwinWith is a theorem of Marcus and Taidosh about finding large grid minors in dense matrices. And this approach applied by Bonnet and others to TwinWith is heavily inspired by a work from, I think, 2011 of Guillemot and Marx, who did the same kind of approach for permutation matrices. They were working on some FPT problem called essentially pattern recognition in permutations. They proved a very nice FPT algorithm for it, and as part of this algorithm, they had a structural decomposition for classes of matrices, and this was the main toolbox. And this tool from Guillemot and Marx was ported by Bonnet and others to the setting of TwinWith and lifted to the proof of this implication number 2 of the theorem we are proving. Yeah. So what is this Marcus-Taidosh theorem about? So imagine you've got a matrix A. Yeah. And I would like now to speak about something simpler than mixed minors. I will call them grid minors. So a grid minor in matrix A is like a mixed minor. Yeah. So again, I've got a partition of columns and of rows into blocks, and I do not care about the zones being mixed or non-mixed. I just want that in every zone there is at least 1 1 somewhere there. So none of the zones is completely full of zeros. Yeah. So this would be a grid minor in a matrix. Yes. So now the zeros and ones are no longer symmetric to each other. I just consider a zone to be complicated if it is not entirely full of zeros. So you could probably imagine or conjecture that if you have a matrix that has a lot of ones, say linear in the order of the matrix, then you should be able to see such a structure. And this is exactly what the theorem of Marcus and Taidosh is saying. So for every k, there is a bound ck. I think it is exponential in k. Yes, such that whenever you have an n times n matrix that has more than ck times n ones, so the number of ones is like super linear. It is at least n times this bound depending on k, then you will be able to find such a k times k grid minor. Yeah. So this tells you that if the matrix is dense in some sense, then you will be able to find such an obstruction. Yeah. So now the idea of the proof of this implication number 2 is that a zone is mixed if it has a corner. A corner is like the 2 by 2 mixed matrix. Yeah, so a zone is not horizontal or vertical if you can find such a small 2 by 2 matrix there, like that, or any like a corner where you do not have the same rows or the same columns. And the idea is that we'll be able to employing a greedy procedure that will iteratively contract convex blocks of rows and columns. And if the procedure gets stuck at any point, it cannot proceed further maintaining some invariant. Then there will be many corners in the matrix. And if there are many corners in the matrix, then essentially looking at Marcus-Taidosh theorem, there will be many ones in some sense. And by Marcus-Taidosh, you will be able to find a mixed minor. So essentially, we will be applying Marcus-Taidosh, but we will be interpreting the ones in Marcus-Taidosh as corners for the purpose of mixedness. Good. Okay, so maybe I will just show you the procedure and give you some intuition why this procedure does the job. So we will be doing. We are going to make a contraction sequence. Yes, so we are starting with with the full graph. Yes, so in a sense we are starting with a partition of the vertex set where every vertex of the graph is in its own part. Yeah. Recall that now these parts are being ordered. Yes, because we've gotten a good ordering on the vertex. Yes, so you can imagine this as the adjacency matrix being like discretely partitioned into blocks of size 1, column blocks of size 1, and discretely partitioned into row blocks of size 1. Yeah. So now the idea is that we will iteratively remove those dividing lines between consecutive blocks, and in this way, by removing the dividing lines, this corresponds to merging blocks in pairs. Yeah? So exactly as in the contraction sequence. So at every point, what we will be having a matrix with some partition of the rows, columns into blocks, and some partition of the rows into blocks, and this partition will be actually always the same. Yeah. And the invariant is that whenever you are looking at one particular block of rows and every particular block of columns, then you will never see too many mixed zones in this row. Yeah. Also, you need to be a little bit more careful. Instead of just looking at the number of mixed zones, you also want to bound the number of mixed borders. Yes, and a mixed border is a border where there is a corner in between, and a mixed zone is a zone where there's a corner inside. Yeah. So now, what you want to do, you want to now prove that you will be always able to find two consecutive blocks of rows or two consecutive blocks of columns that you can merge together while maintaining this invariant. So essentially what happens if I, for example, if I merge this block of columns and this block of columns, this corresponds to removing this dividing line between them. Yeah. So now some of the zones could have been merged, like in pairs. Yeah. So suddenly in this new block of columns, I can find more mixed zones. So I would like to maintain the invariant that in every block of columns and every block of rows, I only see a small number of mixed zones and mixed borders. So I need to prove that there is always a way of doing this join that doesn't break the invariant. Yeah, and the key thing is that if there is no such pair, if I am stuck in the procedure, if every possible merge of two consecutive rows and two consecutive column blocks and two consecutive row blocks gives me too many mixed zones, yes, then this means that there is a lot of mixedness in this matrix. And since there's a lot of mixedness, yes, there will be a k times k grid minor. So maybe we'll not go, because there's not much time. Maybe we'll not go too much into this this argument. But the idea is that because of if no joining is possible for every possible pair of consecutive column blocks or pair of consecutive row blocks, this means that there is a lot of mixedness in the matrix. And we can apply the Marcus-Tardosh theorem to get a large grid minor in terms of the existence of corners, which gives us in the original matrix a large k times k mixed minor. So this was a let's say a sketch of a proof how Marcus-Tardosh is being applied here. But so there are still some technical details that you need to care about. Inside here, inside this argument, because like horizontal and vertical zones are not exactly what we wanted for in the contraction sequence, but essentially I wanted to convey to convey this main intuition, that what we are doing, we are making a greedy procedure. And the greedy procedure tries to contract things, keeping always that in every row or column of this contracted matrix, there is a small number of mixed connections. And if the procedure gets stuck, this is because there is a lot of mixedness in this in the current state. And then by Marcus Tardos, we can find a large mixed line. Good. I still have one thing I want to say for the first part, but maybe we'll make a break because I guess that you are also quite tired. At this point, I wanted to still say something about application of this to get a small twin width of H minor free graphs, but maybe we'll start with this after the break, and then we'll proceed to model checking.
So thank you, Michał, very much for this first part. We're looking forward for the second one, but still there's time for discussion in the program right now. So maybe
so my plan was to have a little bit longer first part and a little bit shorter second part. So maybe we can have now the discussion, make the break still 20 minutes, and shorten the second half by 10 minutes. This is my proposition. Yeah, sorry, I should have told you this before, but this was my plan from the start.
Okay, it's fine, everybody. And so now there's time for discussion. So maybe we can address some of the numerous questions which were posed during your talk in the chat. Or if there are some other questions, maybe.
Yeah, I have a question. Can you hear me?
Sure. Yes.
Yes. Hi. So I wanted to ask, I didn't get all details of the proof, obviously, but does this mean that if you have a partition on the, an order on the vertices, there is a way to construct greedily a contraction sequence, which is not too bad?
Yes, exactly.
Okay.
Yeah, by just applying, if you have an order on the vertices, this gives you a polynomial time algorithm that sequence, and if it fails because it uncovers a mixed minor, sorry.
So if this algorithm fails, I mean, there exists an order such that this algorithm gives something which is not too much worse than the optimal bounded, the optimal twin width contraction, or is this?
So it's like that. If you have a graph together with the order, yes, you can apply the algorithm on the order and get a contraction sequence, or a proof that this order is actually having a large mixed minor. But you still need to have the order in the first place.
But does there always exist an order that corresponds to, or at least functionally, the best possible, the twin width?
Yes, because, there was also this proof of the first one, of the first part. Yeah. If you have a contraction sequence, you can turn it into an order, yes, which is at most twice worse than the contraction sequence.
I see.
If you have the order, you can turn it back into a contraction sequence, at most doubly exponential worse than the largest size of a mixed minor. Yeah. Okay. So these two things are functionally equivalent. However, both of them assume that there is kind of a decomposition given. In one hand, the decomposition is a contraction sequence. In the other case, the decomposition is a total order.
Okay, thanks.
So there are two questions in the chat from Sandra. So is there no known infinite family of cubic graphs with unbounded twin width? So there is no family of all cubic graphs.
So the set of all cubic graphs is the one. There's no known direct construction of a family of cubic graphs with a proof that they have unbounded twin. The only way we are able to prove that cubic graphs, maybe I can actually say this. This will be also mentioned later on. The only way we are able to prove that, maybe here, that cubic graphs have unbounded twin width is that if you think about n-vertex cubic graphs, and they are labeled with 1 up to n, and you want to understand how many of them there are roughly n factorial to the power 3/2 different ordered cubic graphs. However, on any class of bounded twin width, so these are cubic or subcubic. However, if you have any class C of bounded twin width, then the total number of graphs that can be in such a class is at most some C power n times n factorial for some constant C depending on the twin. Yeah. And this follows actually from various tools also related to those mixed minors. So in a sense, bounded twin width classes are called so-called small classes, in the sense that the number of labeled graphs in them with labels 1 up to n is at most n factorial times single exponential in n. And simply the number of cubic graphs is larger. And this is the only argument we have at the current point to say why cubic graphs do not have bounded twin width.
So there's a comment by Anush. Maybe a class of cubic expander graphs gives an example.
I don't think that we know such a class so far.
So there are classes of cubic expanders which have bounded twin width.
Yes, but we do not have a class of cubic expanders with a direct proof that they have unbounded twin width. Yep.
So also Dimitrios asked a question. Are there functions f and f prime and an algorithm that given k and a graph G either outputs an identification sequence certifying that twin width is at most f of k, or outputs a k mixed minor running and with run-in time FPT time?
Yeah, so your question is about FPT approximation of twin width. This is a big open problem. Meaning we don't know how to given any graph that we don't know anything about, how to either say it has unbounded twin width or find a good construction sequence. This would be great, and it would help a lot with all the algorithmic applications.
So I have a follow-up on my previous question. So about this algorithm, so you get an order on the graph, right? And you look at some things, and greedily you do some contractions. But in the proof, there was this stronger invariant somehow that you consider, right?
Yep.
And what does this correspond to? Is this some kind of another type of edge that you look at, or small neighborhoods, or?
So, but you mean this invariant that whenever you see a block of rows, then there is a small number of mixed.
I mean, what I have in head, but I maybe have a wrong idea of the proof. But you had these corners, and you need not only to count the corners, but also to look at other things. And I was wondering does this correspond to, because when you do the contraction sequence, you have these red edges. And do you need to look at something else than just red edges to know greedily what to contract? Or
because yes.
Okay.
So there's a technical caveat in this proof that I now have hidden under the carpet by not saying anything about it, and that there are 3 types of zones. There are vertical, there are constant zones. So this corresponds to 2 blobs having a pure connection. There are vertical blobs and vertical zones and horizontal zones, which are still impure connections, but somehow very nicely almost pure. And there are mixed ones. Yeah. So we need to take care of the horizontal and vertical zones, because they are, from the point of view of a contraction sequence, they're considered impure, while from the point of view of this greedy procedure, they are considered simple already. So they need to be there need to be some post-processing that I have not spoken so far. Yeah.
I see. Thanks.
Yeah.
Thank you.
Yeah. Yeah, actually, I am a little.
So you could define like some other colors of edges and which would refine impure. Yeah, and then define. Yeah, okay.
You can think about, let's say, semi-pure edges, which correspond to a horizontal zone and vertical zones. If you see this on the picture, this corresponds. This is a very already simple situation where you have two blobs, and one of them, like half of the vertices are seeing everybody on the other blob, and half of the vertices are seeing nobody in the other. Yeah. So this is how a horizontal or vertical zone can be understood in graph theoretical terms. So from the point of view of blob interaction, this is an error. From the point of view of the contraction of the greedy contraction procedure, this is considered to be simple. So this needs to be taken care of in the argument. And I do not have really a good understanding of a good intuition why this problem pops up, I must say. I would be happier with a cleaner proof in a sense, without this technical caveat.
Okay, thanks.
Yeah.
So I think my understanding of this is that you could actually relax this instead of strengthen this requirement. Here you have like that there one blob has at most two different types over the other blob. So there are two different types of vertices in one blob with respect to the other ones, the other blob, the adjacent ones and the non-adjacent ones. You could relax it to saying that there's a bounded number of types, bounded number interaction between the two blobs.
Yeah.
And
this is equivalent by twin with 4.
Yes, this is equivalent. So you could relax this to having like the two blobs having a bounded number of different interactions between the two blobs. Whereas the contraction sequence goes in the opposite direction and tries to get exactly pure interaction between the two blobs, which is very nice for various purposes, but from a certain perspective, it's more natural to relax it and allow a bounded number of different interactions between the two blobs and live with that. So you can further refine this to get homogeneous, so pure relationship between the two, but this requires changing the order of the vertices. And this is, so if you start with that's the sort of artifact of the proof, that if you start with this good order where you don't have a large mixed minor and you do this greedy procedure, in order to eventually obtain a good contraction sequence, that you will arrive at a contraction sequence, but in this contraction sequence, it will not really respect this order that you started with. It will have to be somehow rearranged. The graph will have to be rearranged in some way, because we want to further obtain this simplicity that the two parts are pure with respect to each other. If we allow the parts not to be pure but have few interactions with each other, we could live with the same order and obtain a contraction sequence where you have the same order. But well, okay, this is very vague what I'm saying, but it could be. So, but I don't know if it answers anything.
Yeah, but yeah, understanding and working out these proofs is interesting in a sense. This connection to the arrangeability of adjacency matrices. This is underlying this whole theory very much. And in particular, Szymon did some very nice work on this together with Pierre Simon, that is now in the Twin with 4 paper.
Okay, so well, we also need to have a break. So if maybe if there are no pressing questions, we can have a break and maybe further discussion after the second part. So the break will last until, we can't hear you, Michał. No.
Yeah. Now, do you hear me? Now?
Yes. Yeah.
Yes. Yeah.
Helpful. Thanks.
Good. Yes. Thanks. Good. So let's pick up from where we ended. The first part, namely, we have already understood that that twin width, or let's say sketched, that boundedness of twin width is equivalent to the possibility of nicely organizing the adjacency matrix, or in other words, of finding a nice total order on the vertex set of the graph. And then we can use this understanding to prove that certain classes of interest have bounded twin width. In particular, I will try to sketch to you now the application that KT minor free graphs. So whenever you exclude a click on T vertex as a minor, then this implies a bound on the twin width of the graph. Yeah. So just to recall, a minor of say K5. Here it is on the right hand side of the picture. So this consists of five connected sets of vertices that are pairwise disjoint, and they are also pairwise adjacent. So planar graphs are, for instance, K5 minor 3, while KT minor 3 graphs, the theorem of Robertson and Seymour tells us that they are essentially a generalization of planar graphs for a very vast definition of a generalization. Good. So I would like to now to prove to you, or not really prove, but try to convince you that KT minor 3 graphs for fixed T have bounded twin width, and particularly I will prove actually that Hamiltonian KT minor 3 graphs for fixed T have bounded twin width. So I will assume that the graph in question has a Hamiltonian path. So then you could ask, why the hell Hamiltonian path should be of any relevance for boundedness of twin width? And this is would be a very relevant comment. And indeed, this proof can be lifted to a proof without the assumption of Hamiltonicity. But let's assume that the graph in question has a Hamiltonian path. Yeah, so I've got my graph G. P is a Hamiltonian path in the graph, so it's more, maybe it looks like that. Okay, maybe a different color because red is kind of special in our situation. Yeah, so this is a Hamiltonian path P, and I make a total order on the vertex by just ordering by the Hamiltonian path. And so just the first vertex is the first on the Hamiltonian path, then the second, and so on and so on. This is a total order on the graph according to the Hamiltonian path. And I claim that this order on the Hamiltonian path is actually a good order, in the sense that this order will not have a 2T times 2T mixed minor. Why so? So imagine that in this order, in the adjacency matrix induced by this order, you've got a big mixed minor looking like that. Yeah, so each of those zones that you see on the right-hand side here is mixed. In particular, each of them has at least one 1. Yeah, so you always have here 1s in all those zones. So let's look at the first half of rows. So rows 1 up to T, and the second half of columns. So columns T plus 1 through to T. Yeah. So how do they look in the graph? So this rows correspond on the path. Maybe I will draw the path P a little bit more schematically. So these zones here on the path, they correspond to like intervals on the path, while these columns here corresponds also to intervals on the path. And what does those green ones say? They say that between each of those red intervals, there is at least one edge, yeah, to each of the other blue intervals. So now, because this is a Hamiltonian path, yes, I can contract each of the sections on the path, both the red sections and the blue sections, and what I will end up with in this example would be a K33 minor. Yeah, because each of the red ones is adjacent to each of the blue ones. Okay, there is a technical caveat in this argument, in the sense that I drew it like this quite hopefully, that these red intervals will not overlap with those blue intervals, because I asked for the in a minor, I asked for the for those connected subgraphs to be disjoint. So I need that this first T red blocks are actually disjoint with those last T column blocks. Yeah. But yeah, it may actually happen that they would overlap. But if they overlapped, you could easily see that if instead I took the last T row blocks and versus the first T column blocks, then here I would again have a T times T matrix with ones in every zone, which already now would be would consist of pairwise disjoint intervals. Yeah, so either this part of the matrix or this part of the matrix corresponds to rows versus columns, or rows versus columns that are disjoint. Yes, and then one of them gives me a minor of the complete bipartite graph on T vertices on each side. And now you can contract stuff in pairs, vertices in pairs from the different sides, and get a minor of KT, which is a contradiction. Yeah? So this is a very, very quick proof that in Hamiltonian KT minor free graphs, you have the Hamiltonian path give you actually a good order for mixed minors, and now you can turn this good order through the contraction procedure that we had before through the greedy procedure we had before into a contraction sequence for a KT minor free graph with a Hamiltonian path. So it's also interesting to observe what would happen, for instance, on planar graphs here. So here for planar graphs, I would get a contradiction if this was a K33. So this means that I need to start with a 6x6 mixed minor, like this order would exclude a 6x6 mixed minor, which by the procedure that we had before would give me a contraction sequence with red degree, with error degree, at most doubly exponential in 6, which is probably a pretty large number. I did not calculate it, but there is quite a lot of room for improvement here. So one concrete open questions you could ask yourself is, what is actually twin width of a planar graph? Can you get a reasonable upper bound on this? So this proof, as I said, it can be generalized to make the assumption, to get rid of the assumption that mixed minor, that the graph is Hamiltonian. You need to appropriately define a DFS order using a so-called Lex DFS, and this is quite technical actually, but it works. There's also an alternative one-liner proof that twin width is bounded for KT minor free graphs or for planar graphs. Namely, you can quite easily observe that twin width is upper bounded by, or rather, the boundedness of twin width is implied by boundedness of some other graph parameter called the Q number of a graph. I will not define it here, but it is also based on vertex orderings of a graph, and it is actually quite connected to those existence of those mixed minors or grid minors. And boundedness of Q number implies boundedness of twin width, and it is known that KT minor free graphs have bounded Q number. Unfortunately, the proof of this result is, I think, 2 years old. So it is a very recent result, and this one involves quite some machinery about KT minor free graphs. But the interesting point about this alternative proof is that actually this proof gives you a very different order than this one. So it seems that there are multiple different orders that are good for KT minor free graphs, and we still do not understand, do not have a good understanding of this stuff. Good. Any questions about this proper minor closed classes and so on? Otherwise, if you are happy with the proof, please put a +1.
I have a question. So you have sketched to us that graphs, classes of graphs with bounded click width have bounded twin width, and as well, if you exclude minor, KTS minors, is there any other important class for which like proof is missing or like non-trivial?
Like, do we have any reasonable class that we do not know whether it has bounded twin width or not?
We but as people in our talk, so you haven't yet shown this proof.
I don't think so. Meaning the two main examples that that are there that you need to know are proper minor closed classes and class of bounded twin. Oh, Sabi actually has a very good answer. As I said already, cubic graphs do not have bounded twin width. So they're an example, but the division line is somewhere in between proper minor closed classes and a little bit above. So there are cubic expander graphs of bounded twin width, but there are also cubic graphs of unbounded twin width. There is a good question whether classes of polynomial expansion have bounded twin width. We currently don't know this, as far as I know. I will not go into this in this much detail. This requires understanding of polynomial expansion, and but the boundary is still not well defined.
I see. Thanks.
Does the Q number depend on the maximal size of the Q data structure required for a BFS visit of the graph? Q number is a layout parameter, like it is based on an ordering that is about some Qs that you can there. I'm not sure if this is exactly that, but if you do not know Q number, I'm not sure if exactly this is what you mean, but you can probably find it on the web what is exactly this parameter. I don't think I want to go now into the details of the definition of the Q number.
So there are several examples to address Wojtek's questions, but we have seen some of them, like d-dimensional grids. This the proof that Michał showed for two-dimensional grids, you can generalize it to d-dimensional grids, or map graphs. They are also they have bounded twin width. Those are some instances which do have bounded twin width. Yeah, and you can argue that they do. Map graphs is like incidence graphs of
regions in the plane.
Regions in the plane.
Good.
So another question. It seems to be that it's much harder to show that the class does not have bounded twin width.
Yes.
Then is this the case?
Yes, this is the case. We do not have a good machinery for proving that something has unbounded twin width. Essentially, the only machinery that we know at this point is either counting arguments that the class of bounded twin width are small and some classes are simply too rich and need to contain stuff of unbounded twin width. Another thing, and this is what we will be converging into in the second part, is interpretations. Namely, it turns out that class of bounded twin width are boundedness of twin width is preserved under first order interpretations. So if you can interpret something of unbounded twin width, then you need to have unbounded twin width. And in particular, one thing that has unbounded twin width are power set graphs. So a power set graph is a graph, a bipartite graph, where on one side you have a universe of size k, and on the other side you have all the 2 to the k subsets of this universe. And the adjacency is by inclusion simply. Yeah. So this is like a graph that encodes all the subsets of a universe. So then there is a class of power set graphs. So you can prove that power set graphs do not have bounded twin width by a direct argument. And if you are able to essentially interpret using first order logic arbitrarily large power set graphs or other structures in which power set graphs interpret, then you automatically need to have unbounded twin width. This is another way of proving that something has unbounded twin width.
Thank you.
Yeah. Good. So maybe now that we had those questions, we can move to the second part of the lecture, which is the model checking, right? So
I'm sorry, I lost the. I don't see the screen anymore. Maybe it's only my problem. Do you?
Yeah, I just closed the thing. You should see it now.
Yes.
Do you see it? Yeah.
Yes.
Yeah. I needed to change the file because I've got the notes for the second part in the second file. Good. Right. So now we go to part 2, which is model checking and a little bit of discussion of an outlook of what we are now currently thinking about in the area of twin. So now what I will be trying to sketch to you, or rather actually this will be quite a comprehensive proof, I hope, that I will try to give you an algorithm that given a graph G and a contraction sequence of width at most D, yes, and given some fixed first order formula phi, actually a sentence probably. So this is a first order sentence. I will be able to test whether the graph satisfies the sentence in fixed parameter, linear fixed parameter type. So the algorithm will run in running time that is linear on the size of the graph, and then there will be some factor depending on the twin width and some caveats about this. As we already discussed after the first lecture, it is currently very much open whether there is an FPT approximation for twin. Namely, whether given a graph, just the graph, I can produce some reasonably good contraction sequence or reasonably good order for this graph. Yeah. So in this theorem, I assume that such a contraction sequence is given. Yeah. So far we are unable to lift this assumption. One thing that we will be doing during the proof, instead of finding one algorithm that works for every possible D and for every possible phi, I will try to concentrate on giving a so-called non-uniform FPT algorithm. So I will assume that phi and D are fixed, and I will try to make a linear time algorithm. Yeah, so the algorithm can have stuff hard-coded depending on phi and D. This is just for technical purposes, and this assumption can be get rid of. You can get rid of it. Good. So assume that phi and D are fixed. I want to find a linear time algorithm that, given the graph and contraction sequence, tests whether the graph has satisfies the sentence. So the proof of this theorem was given in the Twin with One paper by Bonnet and others. The proof that I will now try to present to you, this will be a different presentation of the proof. I mean, it will, in essence, be the same. However, it will be presented differently. So when you open Twin with One paper, you immediately see that there is something a little bit suspicious, that you do not see the standard keywords like types or errand for phrase game or something like that in the proof. However, once you start to read the proof, you see that there are notions that have the same functionality. And so together with Jakub Gajalski, Rose McCarthy, Felix Leidl, and with Szymon, last year we sat down and tried to reinterpret the proof in the more usual terms of, let's say, errand for phrase games. And well, this is the outcome of our thoughts. It is not published anywhere, but I hope that this presentation can, at least for this crowd, be a bit more accessible. Good. So this is where the proof comes from. But for the details, please look at the Twin with One paper. It's essentially the same proof there. So the basic objects that we will be working with, well, it's a graph G that we are working with, and we are working with a contraction sequence. So at every point in the contraction sequence, I've got this trigraph that is currently in the contraction sequence. And this trigraph, the vertices of this trigraph, they correspond to those blobs. Yes, that are parts of the vertex set that are currently contracted. So there will be always a partition of the vertex set, call it P, And there will be this quotient trigraph where every part is being identified into a single vertex. And then we put an edge between the two parts if they are complete to each other, and non-edge if they are anti-complete to each other. And we put a red edge or an error if their adjacency is mixed. Yeah? So now we have a contraction sequence. We are given a contraction sequence, P1, P2, and so on up to Pn, where the first partition is just a partition into singletons. So every vertex in a separate part. And then we contract until we get the coarsest possible partition where the whole vertex is in a single part. And then every next partition, yes, is being obtained by from the previous one by taking two parts and merging them together by identifying. Yeah, and this exactly corresponds to this contraction sequence on the trigraph. Yeah, and the assumption that we have about this object is that each of those intermediate trigraphs, G over Pi, has red degree at most D. Yeah, so every blob is always in a mixed relationship with D at most D other blobs. And what will be commonly like of interest for us is this red graph. Yeah, so here are the blobs, and now I focus only on the red edges. Yeah, so I look at all the mixed connections between the blobs, yes, and the distances in the red graph, the adjacencies in the red graph. This is what is important for us. Yeah, because the edges and the non-edges represent pure connections that are simple, and the red edges represent connections that are actually interesting. Good. So yeah, let's fix some number q, which will be which eventually will be the quantifier rank of our sentence phi that we are working with. And let's consider some kind of such a situation. Yeah, so we have this partition into blobs, and we have some red graph between them. So now we will be talking about like local situations in this red graph. Yeah, a situation that is only concerning blobs that are sort of close to each other in this red graph. Yeah, and for this I will need the following notion, and this is notion that it is a little bit unfortunate that I need to introduce it at the beginning, as it will turn out a little bit later why we define it in this way. This will actually, the way that this is defined is very important for the proof to go through. And if you know the proof of Geifmann's theorem, this is exactly what is happening. So a sequence of parts, yeah, a sequence of blobs is called local if the following condition holds. So say that here is the first guy in the sequence, A1. Yeah. Then the second one needs to be at distance, say A2, needs to be at distance at most, say 2 to the q minus 1 from the first one. Then the next one, A3, needs to be also quite close to A1 and A2. More precisely, it needs to be at a distance at most 2 to the q minus 2 from at least one of them. Yeah, so from one of them, it needs to be at distance 2 to the q minus 2. Then A4, sorry, needs to be at distance again half shorter from one of the previous ones. Yeah, at most 2 to the q minus 3, and so on and so on. Yeah, so observe that those distances I am asking about are getting smaller and smaller with the consecutive terms. Yes. However, then every next guy needs to be at some kind of vicinity of the previous ones. Yeah. So this is a local sequence. Yeah. And here, these are parts of the partition, so they are blobs. And whenever I'm talking about distances between parts, I'm always talking about distances in the red graph. Yeah. So here, these are actually parts that are close to each other in the red graph, but there is this quite delicate condition on their mutual distances. Good. So this is the definition of a local sequence. Maybe any questions about this definition? Oh, I see that there is some comment that the volume of my voice is changing a lot when you move. Could I check my microphone? I'm not sure if I can check my microphone. I can try to move less, simply. I hope that it will be better. Good. Are there any questions about this definition of a local sequence? And if this is clear, then please put a +1 so that we are on the same page.
Could you recall what is Q?
Q is some fixed parameter, but you can think that Q is equal to the quantifier rank of the formula that we are trying to model check.
Thanks.
In particular, you want P is smaller than Q.
Yeah, P is smaller than Q. Sorry, I forgot to write.
So the sequence can be at most Q long, or what happens if?
Yeah, P is at most Q. So so this is a sequence of length at most P. Oh, at most Q. Any more questions? Okay, if not, then let's continue. Essentially, this is somehow a preparation for understanding possible moves in some local game of inference. This is a spoiler, let's say. Okay, so now we are going to, when we have this local sequences, we are going to somehow think about local formulas. So first of all, we'll speak about partition formulas. So a partition formula is simply an F4 formula that is working on this graph G together with a partition P. But whenever I am doing any quantification, I always assume that the quantification is guarded by which part I am quantifying over. Yeah. So in particular, there's a lot of different F4 formulas because the partition P can have a lot of different parts. But an N4 formula is partitioned if whenever I'm saying there exists a U from some part, there exists a U, I need to specify from which part I expect this U to come from. So this is just a partition formula. So a partition sentence of quantifier rank at most Q is local around some part. Yes, if essentially it speaks about this part and its local neighborhood. So more precise, if I have here my part B, and my formula needs to be local around B, then whenever I have like a chain of nested quantifiers in the formula, you can also think that the formula is in pre-next normal form. It doesn't matter that much, but in a sense, you can also see about look at different like chains of nested quantifiers. Then the consecutive sets I quantify over, they need to form a local sequence around B in the sense that they start at B. Yeah. So the first quantification needs to be at B. Yes. And then I need to quantify in some vicinity of B, so at distance at most 2 to the Q minus 1. Yeah. Then I need to quantify within distance 2 to the Q minus 2 from one of them. Then within distance Q to 2 to the Q minus 3 from one of the previous ones, and so on. Yeah. So this is a local formula. Yeah. When the sequence of quantification is local. Yeah. So then you can easily see that the total number of partition formula can be very large because it depends on the partition P, which can have very many different blobs. But whenever I'm thinking about one particular blob from my partition, then there is only a bounded number of non-equivalent local sentences around B. Yeah. Why? Because well, it's a standard argument that in first order logic for a fixed quantifier rank, there is only a bounded number of non-equivalent sentences, which is the base of the finiteness of the number of types. Now our partition formulas are also saying from which part a particular variable is coming. And if now I am local around B, yeah, this means that I can quantify only over parts that are at distance at most 2 to the Q from B. And because the red graph has bounded degree, this means that there is only a bounded number of such parts. Yeah. So the parts that you are quantifying over, they come only from a finite set if you are having a fixed B. So there is only a bounded number of non-equivalent local sentences around a fixed part. Good. Yeah, so these were the local sentences. So we can now try to make some examples to get a little bit more accustomed with how those local sentences work and behave when we are doing various things with those trigraphs and with merging of those blobs. So first of all, let's look at the two extreme partitions. Yes, the last one when we are having only one part, the whole vertex set, and the first one which is a discrete partition where every part is a singleton. So for the remaining for when we have only one part, then essentially just saying for every vertex u in the vertex set just means nothing, in a sense, like this is not guarded at all, right? And the same for existential quantification. Yeah. So this means that essentially now partition formula, if the partition consists of only the whole vertex set, this becomes all the FO sentences on the graph. And therefore, understanding what local sentences are satisfied at the last moment when we have only one part in the partition, this essentially means that we understand what FO sentences of quantifier rank Q are satisfied in the whole structure. Yeah. On the other hand, yeah, at the very beginning, when I have only singleton parts are always pure towards each other. Yeah? Because if I have a vertex and another vertex, and they are they comprise their own blobs, yes, then they are either adjacent or not, which means that there is either a non-edge or an edge between them. There cannot be any red edge. So there are no red edges at the beginning, which means that those red distances in the red graph are always like either 0 or infinity. So a sentence that is local at a part consisting only of vertex u essentially speaks only about this vertex u. It cannot quantify over any other part. Yeah? So this means that the local sentences here sort of trivialize to sentences that speak only about single vertices. So these two examples suggest that we should be thinking about local types. Yeah, so sets of formulas that are local around every particular blob during the contraction sequence and that are satisfied. So more formally, if I have at some point a partition P, so say Pi, yeah, and I'm having some part B from this partition Pi, yeah, then I say that the local type of this part B is the set of all the FO sentences that are local around B. Well, have quantifier rank at most Q because this is a sentence that we care about during this whole algorithm, and that are satisfied. Yeah, so this is a local type. Yeah, so all local sentences that are currently satisfied around some part. Any questions about it? This is a crucial definition, so please put a +1 if you understood it, and if you didn't understand it, please ask a question for clarification. Okay, I see some number of +1s, but it is getting slower and slower in a sense. Maybe I can clarify something. +0.9. Good. I hope that maybe this remaining 10% will come later when we actually start to work with those types. Good. So essentially now observe that if the types at the first partition, at partition P1, call this that maybe just to make the notation a little bit lighter, that the type I be the type at the moment, at the time moment I. So at the type with respect to the partition Pi. Yeah. So then the type at the first time moment, at the first time step are trivial to compute, yes, because they speak, then the local sentences speak only about single vertices. Yes, so they quantify only about single vertices. So I can just say which sentences are satisfied in those one vertex graph and which are not. Yeah, so they are trivial to compute. On the other hand, if we are able to compute the last type at the end of the contraction sequence, yes, so the type for this partition Pn, which has only one part, the whole vertex set, then this gives us answer to the model checking, because this type consists of all the sentences that are satisfied in the whole graph of quantifier at most q. So then I can just check whether my formula phi is in this set or not. So this means that in this sequence of these type functions, yes, so these are essentially just like data structures which tell us which blob which has what type. It suffices to show how to compute from the types at the first time moment, the types at the second time moment, then what are the types at the third time moment, and so on and so on. And at the end, we will compute what is the FO type of the whole graph. Yeah, so the idea here is to really make this aggregation of type along the contraction sequence. Yeah. Any questions about this plan?
Yes, you start with an FO sentence, and then you want to turn this into a local sentence around B by taking a big disjunction in the first for the type 1, which is trivial to compute. Mm-hmm. Is that what you do? I mean, you start with a sentence which has normal quantifiers without referring to the partition, right?
Yeah, but like about the sentence phi, yeah, that I would like to model check. Mm-hmm. Yes, I will read it from the last type, because the last type consists of partition formulas or local formulas that are for this one big vertex set, which is now one big blob. So what are the partition formulas for this one big blob? They just say there exists a vertex belonging to the vertex set. Mm-hmm. So this type contains all the information about which FO sentences of quantifier rank Q are satisfied in the whole graph.
Yes, but that's the the type N, the last one in the list, right?
Yes.
So that's not the one that's trivial to compute.
Yeah, the one that is trivial to compute is here.
Yes, and that's not for your original formula, but no. That's for, okay.
Yeah, I care about the original formula that I'm asked about only at the very last. I will compute all the types, so all the formulas that are satisfied around every blob all the way through the contraction sequence.
So do I understand correctly that your assumption that your formula is what's called partition-wise or somehow, then it allows, so you strengthen your induction assumption in a sense, but finally it doesn't matter because finally you have one big blob. So if you don't strengthen it, is it also possible to prove it, say, by induction and more complicated, or it's just not true?
I think it will sort of break in a sense, because in a sense I think about this proof as aggregation of information. At the beginning, I have only trivial information. I only know what are the vertices. I mean, if they were colored, the type of the vertex would say what is its color, for instance. So I have only very local information about single vertices. And then the contraction sequence, essentially what it does, it merges different parts of the graph. Okay? So then when I'm merging two different parts of the graph, I'm merging the information about it. Yes, and this information is being kept in the local type. And what we will be doing, we will be, during the contraction sequence, when merging the parts, we will be aggregating the information that we have about FO on this parts, eventually reaching the understanding of what FO sentences are satisfied on the whole graph.
Okay. May I remark, this is very similar to the composition method, where you, for example, want to compute the type of a tree. So you compute the type of the left subtree, the type of the right subtree, and you conclude that you can determine the type of the the whole tree. And so you go from the leaves up to the root. And this way you aggregate this information. So this will be the same thing here, but there's more complicated interactions due to the red edges.
Yes. So the idea here is that if there were no red edges, then essentially you would just aggregate because everything is pure, and like stuff from this part and stuff from this part behave in the same way. They are indistinguishable if you look at the other side. But now the idea is that if you have a bounded degree in terms of the complicated interaction, you can still do it along the contraction sequence.
For the graph distance measure, you only count the red edges?
Yeah.
Okay.
Yeah, it's the distance in the red graph.
Mm-hmm.
Always the distance in the red graph. Yeah. Okay, so maybe we can continue with the
sorry, just one more. But this means in the first step you have an empty graph, no red edges at all, right?
Yeah, no red edges at all.
Okay.
And all the blobs are single vertices, and therefore their types are
and any two blobs have distance infinity. So okay.
Good. So now the kind of strategy is clear, and I already told this. So we are going to compute the types at time step I+1 from the types at time step I in constant time. Yeah. So all these types will be computed from all those types in constant time. And the idea is that a contraction is kind of local in the sense that you are doing an identification of two blobs. And the only blobs that can be, whose types can be affected by this contraction, yeah, by this identification, are, so for example, if you are contracting a blob A with a blob B, yes, then the only blobs that can be affected by this are, whose types can be affected by this, are blobs that are at distance 2 to the q from one of them. And there's only a constant number of them, bounded number of them, because the red degree is bounded. Yeah. So there will be only a bounded number of blobs that are affected, whose types needs to be recomputed when doing a contraction. Yeah, that need to be changed. And we will be able to show that if I am seeing any blob, call it C here, then by analyzing what is this situation in the neighborhood of A, B, and C, we will be able to exactly determine how the type of C needs to be recomputed. Yeah. So this is, and the type of C will only depend on the types of the blobs in the vicinity of A, B, and C, and also on the edges and non-edges between them. Yeah. So in this way, we will be able to update the types when going one step in the contraction sequence in constant time. The number of time steps is linear in the size of the graph. So all in all, I will get a linear time algorithm. Good. So that's the plan. But now, in order to execute this plan, I need to get a more understanding of local types and how to handle them and how to work with them. And to work with them, I will need to use the usual tool of working with types and logic, namely Ehrenhoff-Resse games. So I hope that you are familiar with this classic Ehrenhoff-Resse games, say for first-order logic. This will be very similar for this, but it will be somehow tailored to the local types that we have. Yeah? So imagine that I've got some graph G together with a partition P, and I've got another second structure consisting of a graph H and a partition Q. So that when I'm making the quotient trigraphs, they are actually isomorphic. Yeah, so there is some isomorphism phi that tells me which parts correspond to which parts here. Yeah, and this isomorphism should preserve the edges and the red edges and the non-edges. So now, if I have such two structures, yeah, together with partitions, I can think about the natural Ehrenhoff-Resse game for partition formulas. So in this natural Ehrenhoff-Resse game, the spoiler works as usual, so picks say one vertex in one side, and then the duplicator needs to answer in the other on the other side, but she needs to answer in the respective part. Yeah. So whenever spoiler picks a vertex from say part A, the duplicator needs to answer in part phi of A. And similarly here, if the spoiler picks a vertex here in this part, then the duplicator needs to pick a vertex in the part that corresponds to that on the other side. And as usual, the goal of the duplicator is to endure for Q rounds of the game, and she loses if the induced substructures by the moves are not isomorphic. Good. So this is a strengthening of the usual learn for Frase game by saying that the duplicator needs to respect the parts, and it sort of intuitively works well with the partition formula. So now, if we have partition formulas, we have also local formulas, and therefore we can restrict the game further by looking at the local game. Yeah. So a local game is played around one part of one graph. Yes, of one partitioned graph, and one part of the other graph. Yeah. So here is G and the partition P, and here is H and the partition Q, and I can play a local game around the part A on the one side and part B on the other. So now in the local game, we are restricting the splitter, yeah, because in the local formulas, the quantity, yes?
I guess B is equal to phi of A, right?
Yeah, sorry. No.
No?
No, I'm now, this will be clear in a moment, but I do not restrict now that the G over P and H over Q are the same.
Okay.
Yeah. Right. So I will say the restriction about the isomorphism in a moment. It will be a little bit more involved. Yeah. So now what I'm restricting, because the local formulas are restricting quantification via those local sequences of bags of blobs. Then I restrict the splitter, yes, so that the splitter needs to pick a sequence that is always local around A and B, A on one side and B on the other side. Yes. So whenever the splitter picks some vertex from some blob here, yes, it needs to be close to A.
Right.
And then
there's
yes.
You started calling spoiler splitter, but it's the same concept.
Yes, okay, this should be spoiler. Sorry for that. I will mix splitter and spoiler quite a lot during this talk, I guess. Good. So whenever a spoiler picks somebody around from some blob, the duplicator needs to also from the corresponding part answer. And what do we mean by corresponding now? Namely, because the game is anyway restricted only to the ball of radius 2 to the q around A and around B, I only require the existence of an isomorphism between those balls. Yeah, so I require that there is an isomorphism, a phi between the trigraph induced by the ball of radius 2 to the q around A and around B. The duplicator is restricted by always needing to answer respecting its isomorphism, while the spoiler is restricted by requiring him to pick a sequence that is local. Yeah. So now, okay, this was a bunch of definitions, but I hope that you can see that these definitions kind of reflect our notion of local sequences, of local formulas, and then you can prove a lemma whose proof we will actually omit because it is standard, that the equality of types, of local types, is exactly a winning strategy for the duplicator in the Q round local game around A. Yeah, so the local types around A and B in those structures GP and HQ are the same if and only if the duplicator wins in this local game. Yeah, and not surprisingly, the game was designed in order to reflect to make this lemma true. Good. Is this clear, or are there any questions about this? Otherwise, please put a +1 so that I'm confident that this is clear. I do not see too many, but maybe I can clarify something. Okay. Okay, I see some +1s. Maybe we can continue. So now we will be proving a lemma that we will actually not use. But this lemma contains all the important points about the combinatorics of what is going on, and in particular, it will show why we defined those local sentences the way we defined them. We will not use this lemma explicitly, but then we will say a few times we do it exactly as in the local global lemma. So the local global lemma says the following. Suppose that I've got a graph G and a partition P, and I've got a graph H and a partition Q, such that those quotient trigraphs are really isomorphic. Yeah. So I don't want now to think about the isomorphism of like balls. I just want them to be really isomorphic. And suppose also that this isomorphism preserves the local types. Yes. So whenever I have a part here, yes, the corresponding part on the other side have exactly the same local type, namely it satisfies the same local formulas around this part. Yeah. Then I claim that the duplicator can turn those local strategies into a global strategy. So then the duplicator can win a Q round partitioned game. Yeah, so a game where she needs to answer in the respective part on these two graphs. Yes. So from the equality of the local types, we know that the duplicator has a winning strategy around every blob, and I now claim that that from this it follows that she can win a game on the whole graph. She can somehow merge the local strategies into a global strategy. Yeah. So in particular, if the duplicator wins the Q round partitioned game, then she just can win the normal Ehrenhoff-Russe game on G and H, because well, in the partition game she's only restricted by just saying what is in which part she needs to answer. So in particular, she wins the Q round Ehrenhoff-Russe game on G and H. So G and H satisfy the same FO sentences of quantifier rank at most Q. Yeah. So this is a really important lemma because it will tell us how to combine local strategies into a global strategy, or how to infer from equality of local types, equality of global types. Good. So let's play. Let's give give a strategy for the duplicator for in this global game based on the local games. So we are the duplicator, and we know that around every vertex we have a local strategy, and now we want to use those local strategies to play on the whole. So after I steps of the game, the situation will be as follows. So there will be some blobs where there were moves of the spoiler, yeah, and the corresponding moves on the other side. So this is a situation in the game, and always in her head, the duplicator will have a partition of those moves into so-called clusters. You can think that clusters are sort of local moves that are close to each other, and in essence the duplicator will follow several local strategies, one for each cluster. Yeah. So in each cluster, the consecutive moves that were, maybe here there was a move number 1, maybe the move number 5 and move number 7, these consecutive moves within each cluster need to form a local sequence. Yeah, local in the sense that that was before. So that there is this delicate condition about the distances in the red graph between consecutive moves. And now the main invariant that we will be maintaining during the play is that the clusters are not close to each other, in the sense that if I take a neighborhood, if I take a cluster and I take neighborhood of radius 2 to the q minus I around this cluster and around every cluster, then these neighborhoods, yes, they need to be disjoint.
So those are neighborhoods in the red.
Yeah, these are neighborhoods. Always when I speak about the distances, these are neighborhoods in the red graph. Yeah. Observe that here the radius I am here speaking about. This radius depends on the number of rounds, on the round number. So at the first round, like let's say second round, because the first there are no clusters so far. But in the first rounds, the radius will be large. I will require the clusters to be far from each other. But every next round, the radius I am speaking about is getting halved. If you know the proof of Geifman's theorem, you should. This should be a déjà vu for you. Yeah. So now we can have the strategy of the duplicator. So there are two possibilities. Yeah. So the spoiler. So the spoiler picks some next move. Say he points to a vertex that is being in a block like maybe a block like here. Yes. And now there are two possibilities. Either this blob is being close to some cluster or far from some cluster. So first imagine that it is close to some cluster. More precisely, there is a cluster C such that this blob is within a radius at most 2 to the q minus I from some blob of this cluster. Yeah? Note that because of the invariant star, these neighborhoods are actually disjoint. So there will be a unique cluster C having this property. Then essentially what the duplicator does, she adds this move, so this blob to the cluster C, yeah, and she just plays according to the local strategy she fixed for this cluster. Yeah, so when this cluster was being established, and this will be happening in a moment, she will also establish some local strategy. Yes, and she just pretends that this move happens within this cluster, happens within this local game here, and she uses the local strategy that was fixed for this cluster to answer. Yeah, so then she has an answer depending on the local strategy within the corresponding block on the other side. So this was one possibility, that the splitter, that the spoiler plays next to an existing cluster. And then another possibility, which actually will happen at the very beginning of the game because there are no clusters at the beginning, is that the spoiler plays on some blob in a vertex in some blob that is far from all the existing clusters. Yeah. Then she establishes a new cluster. She establishes a new cluster consisting of only this move, yeah? And she knows. Well, there is a corresponding part B here. She knows that there is a winning strategy in the game around A. Yeah, around the part where the blob, where the spoiler was playing. So this means that she can now fix the local strategy around this cluster, around this blob A, to be the strategy for playing in this new established cluster. Okay, so now there is a technical, there is an important point. Why the invariant star, that the neighborhoods of clusters are disjoint, why this is maintained? Because it could happen, for instance, that this A here was like just outside of the cluster. Yeah, and now he plays here. she plays in the corresponding back phi of A, and now the ball around this new cluster is being is intersecting the neighborhood of some other cluster, and invariant star is not being maintained. However, recall that the radius that we were speaking about was 2 to the q minus I before, and now in the next round, it will be halved. So this means that if I have now this ball of radius 2 to the q minus I here, and radius 2 to the q minus I around the other cluster, after this round, these balls will shrink to half their radius, and they will be disjoint. So in other words, if the move is outside of the vicinity of any cluster, existing cluster, then after halving of the radius, also the ball around the new cluster will be disjoint with the neighborhoods of the existing clusters. So the property, the invariant star is being maintained. Good. So this proves this local global lemma. Are there any questions to this proof? You can put also a +1 in the chat to make me confident that this is kind of clearish. Okay, I see some +1s. This was the most dense part of the proof. But this is really like a very nice combinatorial view on how to combine local understanding into a global understanding. Okay, so now let's harvest the fruit of this understanding and see how you can recompute the types during merging. So imagine that say I've got my partition Pi, and now I move to partition Pi plus 1, which is obtained from Pi by merging two parts, say A and B. Yeah. Then I want to prove to you that the type of the combined part at time step I plus 1 depends only on the situation around A and B. So more precisely, I'm looking at A and B. I'm looking at the neighborhood of a distance, say 2 to the q, around both of them, and here. This is actually already for playing the game. I look at the neighborhood of a distance 2 to the q from both A and B. Yes, I'm looking at all the backs here. Yeah, these neighborhoods can overlap. They may be disjoint. I do not care that much. And I'm looking at the induced trigraph here. So where are the edges? Where are the non-edges? And where are the errors? Yes. And I'm labeling those guys with the types at moment I. And I claim that what will be the type of the combined blob AB depends only on this situation, only on this information. What is the induced trigraph and how it is labeled with types? Yeah. So how do you prove that this depends only on that? Well, you play a game. So suppose you've got two such situations in, say, GAB and G prime A prime B prime. Yes. And which are isomorphic with respect to this information. So they have exactly isomorphic quotient trigraphs, and they have isomorphic labeling with types. And you're playing a game in order to prove that the type after the combination will be the same. So now this game is essentially a game that can both quantify here and here. Yeah, so it is not a game that was there in any of the types A or B, because A and B can be far from each other in the red graph. But now we can use exactly this idea of combining local strategies into a global strategy, as we have seen in the local global lemma, in order to combine the local strategies around vertices of the neighborhood of A and the vertices of the neighborhood of B, in order to play the game, in order to have a global strategy on this combined neighborhood. Yeah. So this means that this type, whenever this information on the right-hand side is the same, the duplicator has a winning strategy in the local game, which means that the type is the same. So this is a sketch of a proof of the fact that after merging of the two parts, the type depends only on the local situation, on the types that were computed before. And the same happens for every blob here. So whenever I have a blob C in a small ball around A and B, it will be also you can also argue in the same way that what will be the type after the merging will depend only on the type before the merging. Note that this type can change because now the locality changes, because the distances change because of merging of the two parts. However, for every blob D that is somewhere outside of this whole picture, then the type doesn't change, because the local formulas around this D they do not involve at all any part that was affected by merging. So the type is simply unchanged. Yeah. So now the key observation is that this information we've put here is finite. It concerns only a neighborhood with an bounded degree graph of bounded radius and a labeling with a bounded amount of types. So it can be hard-coded in the algorithm what kind of neighborhoods will result in what kind of types at the end. Yeah, there are order of 1 types to recompute. So this means that each step takes constant time, and I've got total complexity linear in n of the whole algorithm by computing first the trivial types at time step 1, and then applying this updating procedure at every step of the contraction sequence. So this essentially finishes the proof of model checking. Any questions?
So can I ask a question?
Yep.
So the essential use of the bounded twin width assumption is that at each stage, the degree of, well, I mean, it's the definition is the degree of the red graph is bounded, and so you have bounded size of the neighborhood in the red graph.
Yes.
And so you can compute the types in constant time.
Yes.
Right. What can we put some other condition other than bounded degree, some other kind of well-behavedness condition on these red graphs, which will allow efficient computation of these types? I mean, because evaluation of first order logic we can do not just on bounded size, of course, but on other kind of sparse graphs.
So I do not have a very good answer to this question, other than it cannot work because every graph has a trivial contraction sequence where the red graph is always a star by just contracting iteratively stuff on one vertex.
Right.
And then the red neighborhood of this vertex essentially consists of all the remainder of the graph.
Right.
Which is super complicated, and you cannot really aggregate this information. You cannot confine it to a single thing. So this is a very valid question. In what sense you can like generalize this red degree being bounded to some weaker condition, but you need to this star example is actually quite prohibitive, and we do not have a good idea of what could be a generalization. Yeah. Yeah. So Jakub is saying that maybe bounding the red degree by something that is not really constant but small could be of some use. I'm not sure about this. I don't remember exactly this discussion, but this doesn't sound like a very promising direction to me, at least now. Because this will blow up in the total number of types. Good. Okay, any more questions? Okay. So I think that I will unfortunately need to skip the part on interpretations, transductions, which is really a pity because this is a part that is currently under development, and it is really exciting. Let me just say one thing about this. So there is a well-defined notion of FO interpretations and FO transductions, which is essentially deriving new relational structures out of old relational structures using first-order formulas. So, for instance, you could turn one graph into another graph by saying what will be the edge set of the new graph by interpreting the edge set of the new graph through a first-order formula in the old graph. There's also a related notion of an FO transduction, which is a non-deterministic procedure, which is like a non-deterministic pre-coloring of the vertices, labeling them with some colors, and then you apply. So then, for instance, classes of bounded click width or classes of bounded linear click width are so-called ideals with respect to those transductions or those interpretations, in the sense that if you have a class of bounded, say, click width or linear click width, and you apply any first-order interpretation to this class, or first-order transaction, if you like transactions more, then you will also get a class of bounded click width or linear click width, respectively. And the same also holds for classes of bounded twin width. So whenever you are having a class of bounded twin width and you apply any first-order interpretation to it, you will still get a class of bounded twin width. So this means that they are bounded twin width is really robust with respect to a first-order logic. Not only you can do a first-order model checking on it, but also this is a concept that is somehow closed under any modification that can be explained in first-order logic. And to get this result, it is not very hard. You need to understand the model checking result and this whole machinery of types. And if you think about it for a while, you can get this result quite easily from just this understanding. It shows somehow tameness of first-order logic on bounded twin width classes. Yeah. Good. So let me say a little bit during the last, let's say, 4 minutes about some open problems, because there's like a billion of open problems that can be asked about twin width. Some of them we have already discussed. For instance, FPT approximation algorithm for twin width. This would be very helpful for all kinds of algorithmic applications. But also, even if you have a say contraction sequence or a total order and so on, you can think about what kind of problems I can approximate or solve exactly on this kind of decompositions. And there's already quite some work in twin width 3 paper on this, and it appears that there is a lot of interesting stuff that you can derive here. So the combinatorics of twin width, well, this notion is 1 year old, so there's a lot of questions you can ask about it. In that twin width 2 paper, there is a proof that classes of bounded twin width are chi-bounded, in the sense that the chromatic number is bounded by in terms of the click number of a graph, but the bound is roughly the twin width to the power the click number of a graph. I will not go into the details about chi-boundedness. If you know this notion, this is a classical notion in graph theory. And there's a very good question, what about getting polynomial chi-boundedness? This seems plausible that this could be the case. But more generally, this is just a pretext to get a better structural understanding of graphs of bounded twin width. In particular, we're thinking for quite a while, we don't know how to do it, about some kind of decomposing a graph of bounded twin width into subgraphs of bounded click width. This could be very helpful for attacking polynomial chi-boundedness. But from the more model theoretic point of view, we already discussed that the graphs of maximum degree 3, so cubic graphs, subcubic graphs, do not have bounded twin width. Yeah? So it would be really nice to have a concept that encompasses both those classes, yes, bounded twin width and say graphs of maximum degree 3, because we know that FO model checking is fixed point retractable on both of them. Yeah? I think that this touches upon a deeper question about having a dense analog of bounded expansion classes. So I don't want to now discuss bounded expansion. If you know a little bit about the theory of sparsity, then you can start to draw diagrams like that, where you have the usual hierarchy of sparsity, and then you can somehow understand what are the dense analogs of sparse notions of of being well organized. So then bounded twin width sits somewhere here above bounded click width. Yes. On the other hand, it is incomparable to bounded expansion exactly because of this subcubic graphs. So then natural question would be, is there any suitable notion here on this part of the picture that on one hand, when you restrict attention to bounded to sparse classes, projects to bounded expansion, on the other hand, it generalizes bounded twin. And yeah, we currently do not have a clue how to define such a notion so that it is natural and well behaved. Okay, I think that this really exhausts what I wanted to talk about during this lecture. So thanks a lot. Are there any questions now? I see that there are no questions still in the chat.
Thank you very much for the talk. So there's one question by Isolde. How about local twin width, bounded local twin width?
Like so you want every neighborhood to have a bounded twin width? Good question. I have no idea.
Well, you can consider it, and it will have, I guess, sort of, if you can compute the decompositions locally, then it will have FPT model checking. But yeah,
so you can definitely define it. If you get a decomposition, you get a FPT model checking. But I don't think that we have now a class that would have local bounded twin width, but would not have bounded twin width. I don't think that this notion is natural at this point.
This would subsume bounded degree graphs because they so it would be a common generalization of bounded degree and bounded twin width.
Yes.
But yeah.
Yeah, but in a sense, yes, you could do it like that. You could probably get also like a low twin width coverings. This kind of definitions would also work. But on the other hand, you want to have some robust understanding of this. For instance, you would like this to be closed under FO interpretations. Yeah. Andrew Kim asks, what is bounded local twin width? Well, you can just say that there is a function f such that whenever you look at the vertex and you look at our neighborhood of this vertex, then the twin width is bounded by f of r.
I see. So yeah, so actually, like, okay, maybe I can mention something about this variance of twin width. So this is an ongoing work which we are working. This is an ongoing work. So we try to consider like variance of twin width, something like, and we could prove something like the following. So if every red component has bounded size, then this is equivalent to have bounded click width. And if
yes, and this I mentioned on the first part of the lecture.
Right, great.
There's an equivalence like that. Yes.
And if you bound the okay, so you were already aware of it. Maybe you heard from one of us.
Well, last spring we spent quite some time thinking about twin width, and this was one of the observations we had.
All right.
At some
okay.
point. Yes.
Yeah. So yeah, you can derive it from from the proof that bounded click width has bounded twin width. Also bounded linear click width, you can characterize it as like the entire number of red edges is bounded.
Oh, nice. Okay, this I did not know.
So now because path width is a sparse case of linear click width. So now you can confine it to the sparse case, and then you get the characterization for path width and tree width. So what we are trying right now is to have some natural variance of twin width for bounded expansion class and potentially nowhere dense class.
So that then if you sort of lift the assumption about the sparsity, you immediately get to
exactly.
Yeah, this sounds interesting. Yes. Nice idea. So just to mention, we in Warsaw were working quite a lot recently on stable classes of bounded twin width, where you do not see a large half graph by interpretation, because they also form an ideal with respect to transductions. And it seems that there is also quite a lot of interesting work that can be done there. Good. Are there any more questions around? Okay, I don't know what happens now.
So, well, I guess we can also do a discussion, a general discussion, if there are not only questions, but any comments and so on. There's a discussion phase predicted in the program, but
maybe a small clapping phase before the discussion phase.
Thank you. Thank you very much for listening and bearing with me for those 2.5 hours. I hope that this was enlightening.
Thank you, Nathan, for reminding me of my most important duty to ask everybody to clap.
You're welcome.
Forgot about that item.
Yes.
Oh, maybe I can continue my comment. Like I forgot to mention, like there is also interesting characterization of minor closed family.
Oh, that's actually
variant of twin width.
Yeah. So essentially, like if you see on the screen now, there is this diagram of those classes, and this one column being the sparse column, and the second column being the dense column, so the dense counterparts.
Yeah.
And like this diagram is almost constantly on my whiteboard in my room, because we are now looking at different parts of this diagram and trying to feel the information and the understanding of different concepts.
So, Ojeng, could you say something about this characterization of minor free?
Oh yeah, minor free. So there is one variant you can consider for twin width is like when you contract. So when you make the contraction sequence, so okay, now I confine myself to a linear ordering which came from some spanning tree of the graph. So meaning that okay, I fix some spanning tree of the graph, and then I will only contract something which appears as an edge in the spanning graph. So if you do that, then and then among all possible spanning tree, you find the optimal one that gives you the smallest twin width. Then that, if this is bounded if and only if the monotone graph class is minor closed.
That's very interesting.
I see.
Yeah. So actually, one direction already is implicit in our first paper. So
yeah, because you do a Lex DFS.
Yeah. So we do this Lex DFS. So the opposite direction is So when you have, so if you're bounded this we call it spanning twin width. So if the spanning twin width is bounded, then let's have this additional partial order as part of your binary structure, and then you can FO interpret the graph class. Yeah, which will include this minor closed family.
Yeah, because if you had now a large if you had a large minor now, then from this tree and the minor, yeah, you would be able to interpret something complicated.
Yeah.
Yeah, that's very nice. That's a very nice point of view.
Yeah, this is pretty nice. So yeah, we are trying to do this for everything on the left column.
Yeah. No. So there's also, let me mention, there is also a very nice result recently. It was in a paper of, it's called, I think, twin width and permutations. that essentially you can think about a bounded click width as things that are transducible or interpretable in 3 orders. And you can also define bounded linear click width as classes that are interpretable in total orders, in linear orders. So then if you know that bounded twin width is also an FO ideal in the sense that it's close under FO interpretation, you can ask for this kind of a characterization about the twin. And there exists indeed one. Namely, if you think about 3 orders, you can encode them in permutations avoiding a fixed pattern. A pattern of one element, then a larger element, and then an element one smaller. You represent a permutation as a relational structure by giving 2 total orders. And similarly, a linear order you can interpret as permutations avoiding just inverse. Yeah, so it's just like that. So now, if you have this this understanding, you see that the linear click width and click width can be understood as classes that are interpretable in permutations avoiding some precise forbidden pattern. And then it turns out that bounded twin width are exactly structures that are classes of structures that are transducible or interpretable from a class of permutation that avoids some fixed pattern. So whatever large pattern you fix, say on 10 elements that you disallow to exist in a permutation, you will whatever you transduce out of it will have bounded twin width, and conversely, every class of bounded twin width can be transduced like that from some class of permutations avoiding a fixed pattern. So this also gives another way of viewing those classes, which is very much a model theoretical, a sort of understanding what is the basic skeleton of adjacent, let's say, relations from which you can interpret the whole structure.
Okay, are there any other comments? So I guess if not, then we can maybe thank Michał once more. And so thank you, Michał, for the
Yeah, thanks a lot for listening to me. It was actually a pleasure to talk about this, because this is a really exciting topic.
Yeah, so I guess we can dissolve.
Yeah. Thanks.
See you in the next meeting. I hope to see everybody in the next Friday afternoon seminar, and in 2 months.
Is there any understanding who will be speaking the next time and when?
So we don't have anybody confirmed, but we have some candidates, and we are determined to make another one. So there will be a holiday break, but when we will, next seminar will take place in October.
Mm-hmm. Good.
Okay.
So we are happy with suggestions who can be a good speaker or a good topic. Okay, thank you very much one more time, Michał and Szymon, and see you next time.
Yeah. Okay. So thanks a lot, and see ya.
See you. Bye.
Bye.